For centuries we believed we lived in a perfect clock. But the universe never had hands. Imagine the sound. Europe, late 19th century. The sharp whistle of a steam train tearing through the cold morning air. The metallic hammering of factories that never sleep. The precise tick-tock of tower clocks marking each second like divine orders. And beneath all that industrial noise, something new, something electric. A barely perceptible hum running through cables newly strung between cities, between countries, between continents. Humanity had tamed the world. Or so it believed. The cobblestone streets of London, Paris, Berlin vibrated with the confidence of a civilization that had named everything. Scientists had dissected light, weighed the planets, calculated the speed of sound. Isaac Newton had delivered the laws of motion as if they were commandments carved in stone. Space was an immense but empty box, a neutral stage where the great theater of existence unfolded. Time was an arrow that advanced relentlessly, the same for everyone, indifferent to the observer. A second in London was identical to a second in Tokyo. A meter on Earth measured the same as a meter on Mars. The universe functioned like a colossal machine, predictable, mathematizable, safe. People lived within that certainty as one lives inside a cathedral. There were eternal rules, causes and effects, order and control. Engineers built bridges ever longer because they knew exactly how much weight they could bear. Astronomers predicted eclipses decades in advance because celestial orbits obeyed perfect equations. Even God seemed to have retired, satisfied, letting his creation run on its own like a well-adjusted clock. But beneath that industrial calm, beneath that scientific optimism, something didn't add up. There were experiments that failed. Results that made no sense. Light traveled through empty space, but waves needed a medium to propagate. So there must exist something invisible filling the entire cosmos. The luminiferous ether, they called it. A ghostly substance, subtler than air, more ubiquitous than water, that sustained light waves as the ocean sustains waves. For decades, physicists searched for that ether. They designed increasingly sophisticated experiments. They split light rays. They measured velocities with microscopic precision. But the ether never appeared. It was like searching for the stage of a theater and discovering that the actors floated in emptiness. And there were more cracks. Small inconsistencies that scientists noted in the margins of their notebooks, uncomfortable, hoping someone else would solve them. Mercury's orbit didn't fit perfectly with Newtonian predictions. A few arc seconds were missing. Nothing serious, perhaps. A measurement error. Or perhaps not. The 19th century needed answers. Not out of academic curiosity but for something more visceral, fear of chaos. Humanity had emerged from caves, had left behind myths and superstitions, had built empires upon reason and calculation. To retreat now, to admit we didn't understand the universe as well as we thought, was unacceptable. It was too similar to darkness. Too similar to being lost again. Travel was accelerating. A train could cross a continent in days. A steamship could circumnavigate the globe in weeks. Communications expanded through the telegraph, transforming time and distance into increasingly insignificant obstacles. Commerce, war, diplomacy depended on that speed. And speed depended on physics. Every kilometer of railway track, every submarine cable, every lighthouse on the coast was an act of faith in Newton's laws. But if those laws had limits, if there was something beyond that we didn't understand, then the entire system tottered. Scientists confronted the invisible. These weren't just abstract equations on a blackboard. It was the very structure of reality that seemed wrong. The problem wasn't missing data. The problem was that the data contradicted logic. Light traveled at a constant speed no matter how you measured it. That was impossible. If you ran toward a light source, you should measure it faster. If you fled from it, slower. That's how everything else worked. Sound, bullets, ocean waves. But light didn't obey. It behaved as if the rules didn't apply to it. As if it knew something we didn't know. And then, amid that collective bewilderment, amid a century that demanded definitive answers but found only paradoxes, a boy was born in a small German town. A boy who years later would do something no one had attempted, not search for the universe in laboratories but in his own mind. Ulm, 1879. A modest city in southern Germany, with narrow streets and sloped roof houses. Hermann Einstein and Pauline Koch celebrate the birth of their first son. They name him Albert. A baby with a disproportionately large head, which worries his mother. A baby who takes time to speak, which worries her even more. Doctors reassure the family. There's nothing to worry about. But Pauline can't help observing her son with a mixture of love and anxiety. Something about this child seems distant, as if he's listening to a conversation no one else can hear. Albert's first memories are fragmentary, as all childhood memories tend to be. But there's one that will mark him forever. He's 5 years old, maybe 6. He's sick in bed with a fever. His father, trying to distract him, shows him a pocket compass. Albert holds it with both hands. He observes how the needle trembles, searches, orients itself. Always toward the north. No matter how he turns the box. No matter how he shakes it. The needle knows where it must point. Albert feels something he can't name yet. It's wonder but also unease. Something invisible moves that needle. Something that passes through wood, metal, air, his own hand. A silent force that acts without touching. The first contact with mystery. That compass stays with him. Years later he'll say it was the moment he began to suspect that behind ordinary things, behind what we see and touch, exists a hidden order. That reality doesn't reveal itself easily. That you must search for it with more than eyes. But Albert's childhood isn't that of a prodigy by conventional standards. He doesn't speak fluently until age 4. He's solitary. He prefers building card houses to playing with other children. When he does, he stacks the cards with obsessive patience, reaching towers of 14 stories. If they collapse, he starts again without frustration. His sister Maya, 2 years younger, observes him with fascination and some fear. Albert has violent tantrums when something disturbs him. He throws objects. He screams. But then he calms down and returns to his usual silence, to his inner world where no one can enter. The family moves to Munich. Hermann opens an electrical equipment factory with his brother Jacob. These are years of optimism and precariousness. Electricity is the future, everyone knows it, but the business is unstable. There are contracts won and lost. There are nights when Hermann returns home with his face tense, calculating numbers in his head. Albert observes everything from his room. He hears adult conversations about money, about competition, about the weight of maintaining a family. He learns early that the world doesn't forgive those who fail. At school, Albert is an irregular student. Brilliant in mathematics and physics, mediocre in almost everything else. Teachers describe him as rebellious, insolent, disrespectful of authority. The German educational system of the era is rigid, authoritarian, militarized. Teachers expect blind obedience. Students must memorize, repeat, never question. Albert does the opposite. He asks why. He points out inconsistencies. He refuses to accept answers that don't make sense. One teacher tells him he'll never amount to anything. Another temporarily expels him for subversive attitude. For Albert, school isn't a place of learning but a prison of thought. But there are exceptions. An uncle who lends him science books. A medical student who comes to dinner on Thursdays and talks to him about philosophy, about Kant, about the nature of knowledge. And above all there's Max Talmud, a young Jewish student who becomes his informal mentor. Max gives him a geometry book. Albert devours it in weeks. Mathematical proofs fascinate him. They're like mental card houses, but ones that never collapse. Each theorem rests on the previous one. Each conclusion is inevitable if you accept the premises. It's the first time Albert feels he understands something perfectly, without doubts, without ambiguities. Mathematics doesn't lie. It has no opinions. It doesn't change depending on who observes it. Pure, clean, true. While others memorized formulas, he imagined riding on a beam of light. He's 16 years old. He's in physics class. The professor explains something about electromagnetic waves. Albert stops listening. His mind has escaped to another place. He wonders, what would I see if I could travel at the speed of light? If I could run as fast as a light beam, how would another light beam beside me look? According to Maxwell's equations, light is an electromagnetic wave. But if you travel alongside a wave, shouldn't it appear static? Like running beside a moving train and seeing it still. However, Maxwell's equations don't permit static waves. So something is wrong. Either with the equations or with the idea that you can reach the speed of light. But why couldn't you? Albert has no answer. Not yet. But the question haunts him. It's the type of question you can't solve with an experiment. You can't mount a light beam and see what happens. You have to imagine it. You have to build a laboratory in your head where the laws of physics are the only materials. It's a thought experiment. A term that will become famous thanks to him, but which at that moment is just the natural way his brain works. Thought experiments aren't Albert's invention. Galileo used them to demonstrate that all objects fall at the same speed. Newton used them to imagine what would happen if you fired a cannon so powerfully that the ball circled the world. But Albert takes them further. For him, disciplined imagination is more powerful than any laboratory. Because you can control all variables. You can eliminate friction, noise, human error. You can see directly the logical structure of the universe. But life doesn't reward imagination so easily. At 17, Albert leaves the institute without graduating. He can't bear another year of Prussian discipline. He flees to Italy, where his family has moved after the electrical business failed in Munich. Hermann and Pauline are disappointed, worried. Their eldest son is a school dropout with no clear prospects. Albert promises them he'll study on his own and take the entrance exams at the Polytechnic in Zurich, one of the best engineering schools in Europe. He takes the exam. He fails. He's brilliant in mathematics and physics, that's undeniable. But his knowledge of languages, biology, history and literature is deplorable. The Polytechnic rejects him but suggests he complete his secondary education and try again the following year. Albert accepts. He enrolls in a school in Rewrote, Switzerland. There, for the first time in his life, he finds an educational environment that doesn't suffocate him. Teachers encourage critical thinking. Classes are discussions, not monologues. Albert flourishes. He falls in love with Switzerland. With its mountains, its political neutrality, its freedom. A year later he takes the Polytechnic exam again. This time they accept him. The years in Zurich are complex. Albert is a talented but problematic student. He skips classes he considers boring. He prefers reading on his own in his room or in cafes. He studies Maxwell, Hertz, Boltzmann. Not the textbooks his professors assign, but the original texts, the primary sources. He wants to understand how the greats thought, not what conclusions they reached. It's a crucial distinction. Most students learn the answers. Albert wants to understand the questions. He meets Mileva Maric, one of the few female physics students at the Polytechnic. She's Serbian, brilliant, serious, reserved. She limps slightly due to a congenital hip malformation. She's been discriminated against all her life, for being a woman, for her disability, for her origin. But she's fierce in her determination. Albert falls in love with her. Or believes he does. It's hard to know for certain. His letters are full of intellectual passion, but also possessiveness and selfishness. They talk about physics, about relativity, about unsolved problems. Mileva understands his ideas. She's perhaps the first person who does. But the relationship is turbulent from the start. Albert's parents reject her. Pauline considers Mileva not good enough for her son. She's too old, they say. Too serious. And she's not Jewish. Hermann, more pragmatic, worries about his son's economic prospects. How will he support a family if he can't even graduate with honors? Albert graduates in 1900 with mediocre grades. Not because he's incapable, but because he's invested his energy in things that interest him, not in what they demand of him. The consequence is immediate. None of his professors recommend him for an academic position. In the university world of the era, positions are obtained through connections, through deference, through fitting into the system. Albert doesn't fit. He's questioned his professors. He's skipped classes. He's prioritized his curiosity over conventions. Now he pays the price. For 2 years he searches for work. He applies for assistant positions at universities throughout Europe. All applications are rejected or ignored. He works as a substitute teacher at secondary schools. The jobs last weeks or months. It's unstable, poorly paid, humiliating. Albert feels the weight of mediocrity. He's 23 years old. He's unemployed. His girlfriend is pregnant. Mileva gives birth to a girl in January 1902. They call her Lieserl. Albert never meets her. He can't. He's in Switzerland looking for work. Mileva is in Serbia with her family. The society of the era doesn't forgive unwed mothers. The stigma is brutal. There are no clear records of what happened to Lieserl. She was probably given up for adoption. She probably died of scarlet fever in her first year of life. Albert never speaks of her publicly. Neither does Mileva. It's a silence that will accompany them always. Albert's first great sacrifice isn't intellectual. It's human, intimate, devastating. In June 1902 he finally gets stable employment. Thanks to a friend's recommendation, he's hired as a third-class technical examiner at the Federal Patent Office in Bern. The salary is modest but sufficient. The work is monotonous, reviewing patent applications for electrical devices, clocks, machinery, evaluating whether they're novel, whether they work, whether they merit legal protection. Albert works 6 days a week, 8 hours a day. He's a bureaucrat, a cog in the Swiss state's administrative machine. But it's perfect. The work doesn't require all his attention. He can complete his tasks in a few hours and dedicate the rest of time to his own thoughts. The office is quiet. No one bothers him. No one asks what he's working on. In the evenings he returns to his small apartment. Mileva waits for him. They've finally married in a simple ceremony without their family's blessing. They have dinner. They talk. They discuss physics. Albert fills notebooks with calculations. Mileva checks the mathematics. They're partners, though the relationship already shows signs of tension. Love is becoming habit, and habit becoming obligation. Albert has a routine. He wakes early. He walks to the office. He works. He returns home. He has dinner. He thinks. He sleeps little. On weekends he meets with friends in his apartment. They call it the Olympia Academy, as a joke. It's not a real academy. It's a group of young men marginalized from the academic system who gather to read philosophy and science. They discuss Hume, Spinoza, Mach. They criticize received ideas. They mock the pomposity of university professors. It's in those conversations, in those informal debates, where Albert sharpens his thoughts. Because theories aren't born in laboratories. At least not the theories that change the world. They're born in solitary minds that have the courage to reject the obvious and seek the true. Einstein doesn't have access to expensive equipment. He has no assistants. He has no funding. The only thing he has is time, silence, and a mind that can't stop. During the day he examines patents for machines. During the night he dismantles the universe. The questions he asks himself aren't new. Other scientists are also baffled by the same problems. But Albert has an advantage. He's not trapped in academic dogma. He doesn't have to defend a mentor's reputation. He doesn't have to conform to an established line of research. He can think with radical freedom. And what he thinks is this: maybe the problem isn't in the answers. Maybe it's in the questions. Maybe we're asking wrong. He closes his eyes. He imagines. A train moves along the tracks. Inside the train there's an observer. Outside the train there's another observer standing on the platform. A beam of light crosses the car from one end to the other. Question: how long does the light take to cross? For the observer inside the train the answer is simple. The length of the car divided by the speed of light. But for the observer on the platform, the train is moving. So the light doesn't just cross the car, it also advances along with it. The distance is greater, but the speed of light is the same. Because light always travels at the same speed no matter who measures it. It's an experimental fact confirmed again and again. So, if the distance is greater but the speed is equal, time must be different. The observer on the platform measures a longer time than the observer in the train. Pause. He rereads it in his mind. He checks it. Time is not absolute. Time depends on motion. Time depends on the observer. It's an absurd conclusion. It contradicts all human experience. Two people looking at the same clock should see the same time. That's common sense. But common sense is built upon experiences at low speeds. Trains, horses, boats. We never move fast enough to notice the difference. But if we traveled at a significant fraction of the speed of light, time would literally slow down. Your second would be longer than my second. And we'd both be correct. Albert doesn't discover this in 1905. He discovers it earlier. Years earlier. But he needs time to be sure. To verify the mathematics. To make sure there are no errors. Because if he's wrong, it will be the final humiliation. A bureaucrat from the patent office claiming that Newton was wrong. That time isn't what we thought. That reality itself is different. But he's not wrong. For months he calculates, reviews, doubts. Maliva helps him. Marcel Grossman, his friend from the Polytechnic, also helps. They share ideas. They debate. Albert is obstinate. When something doesn't fit, he doesn't ignore it. He pursues it. Entire nights in front of sheets of paper, searching for the error, refining the argument. His mind becomes the most powerful particle accelerator of the 20th century. He doesn't need to collide atoms. He collides ideas. And then, in the spring of 1905, everything fits together. It's not a sudden moment of illumination. There's no eureka. It's subtler. It's the growing sensation that the pieces are finally in their places. The equations work. The paradoxes resolve. The universe makes sense again, but a different sense than we believed. Albert writes. Fast, almost feverish. Not in the technical language of academic journals, but in a clear, direct, convincing style. The article is titled, On the Electrodynamics of Moving Bodies. It's modest, almost mundane. There are no references to revolutionary theories. There are no grandiose claims. Just a series of logical arguments that lead to inevitable conclusions. He sends it to the journal Annalender Physik. He waits. He doesn't know if they'll publish it. He doesn't know if anyone will read it. He doesn't know if it will change anything. But he knows he's right. His mind became the most powerful particle accelerator of the 20th century. But not because he had access to sophisticated technology. Not because he could split atoms or build giant telescopes. Albert Einstein turned his imagination into an instrument of scientific precision. While others sought evidence in laboratories, he sought coherence in pure thought. While others measured the universe, he reimagined it. Einstein's interior laboratory had no walls. It had no equipment. It required no funding or permits. It existed entirely in the space between his temples. It was a place where he could stop time, accelerate trains to impossible speeds, split light beams, make clocks run forward and backward. It was a mental theater where the laws of physics were the only actors, and logic was the only director. Imagine it. You're at the patent office in Bern. It's 1904, maybe 1905. There are papers stacked on your desk. Patent applications for improvements in synchronized clocks, for electrical measuring devices, for machinery that must function with precision. Your job is to evaluate whether these inventions are viable, whether they deliver what they promise. You review diagrams. You read technical descriptions. You verify calculations. It's meticulous, repetitive work. Most of your colleagues find it tedious. But you find something more. You find patterns. Clocks fascinate you. Bern is full of them. Towers with clocks, train stations with synchronized clocks, factories that depend on temporal precision. The entire city functions like a machine that measures time. And you, sitting at your desk, begin to wonder, what does it mean for two clocks to be synchronized? It seems obvious. It means they mark the same time at the same moment. But wait, what is at the same moment? If one clock is in Bern and another in Geneva, how do you know they're synchronized? You have to send a signal. A light signal, perhaps. But light takes time to travel. Not much, but something. So when you see that the clock in Geneva reads 3 o'clock, it's no longer 3 o'clock. It's 3 o'clock plus the time it took the light to reach you. It's a small detail. Insignificant for practical life. But for Einstein, it's a crack through which all of classical physics seeps. Because if you can't define at the same time, absolutely, then time itself isn't absolute. It's relative to your position, to your movement, to your way of measuring it. Close your eyes. The office noise disappears. You're no longer in Bern. You're on a train. Not a real train, but a perfect train that exists only in your mind. There's no friction. There's no air resistance. Only pure mathematics expressed in imaginary metal. The train advances at constant velocity. Inside the car, everything is normal. You can walk, throw a ball, drink coffee. The laws of physics work exactly as if you were stationary. It's Galileo's principle of relativity. Uniform motion is indistinguishable from rest. There's no experiment you can do inside the car that tells you whether you're moving or not, unless you look out the window. But now add light. In the center of the car there's a lamp. It lights up. The light travels forward and backward toward the ends of the car. For you inside the train, the light reaches both ends at the same time. You measure the distance. It's the same. You measure the speed of light. It's constant. Everything fits. But now imagine you're outside the train, standing on the platform. You see the train pass at high speed. You see the lamp light up. You see the light travel toward the ends of the car. But the car is moving. The rear wall moves toward the light. The front wall moves away from the light. So the light reaches the rear wall first. Not at the same time. For you on the platform, the events aren't simultaneous. Who's right? You inside the train who sees simultaneous events? Or you on the platform who sees them separated? Classical physics says one of you is wrong. There must be an absolute frame of reference, a correct point of view from where things really happen. But experiments say no such frame exists. Both observers measure the same speed of light. Both are applying the same physical laws. So both must be right. The only way both can be right is if time is different for each one. Einstein doesn't discover this by looking through a telescope. He doesn't measure it with instruments. He deduces it. He thinks it through until reality has no choice but to reveal its structure. It's like solving a puzzle where the pieces initially seem not to fit, but suddenly you realize the problem isn't the pieces. It's the way you assumed they should fit. Time stretches. Distance shrinks. Reality bends. These aren't poetic metaphors. They're literal descriptions of what Einstein is discovering. If you travel very fast, your time passes more slowly than that of someone who's still. It's not that your clock is broken. It's that time itself has slowed down for you. Your second lasts longer than my second. If I could see you from outside, I'd see you moving in slow motion. Your heart beating slower. Your thoughts flowing slower. But for you, everything would be normal. Your second would still feel like a second. And space. If you travel very fast, you contract in the direction of motion. You become thinner, more compressed. Your meter is shorter than my meter. But you wouldn't notice. For you, your meter would still be a meter. It would be my meter that would seem strange to you. It's disconcerting. It goes against all intuition. But the mathematics are impeccable. Einstein's equations predict exactly how much time dilates and how much space contracts. And most importantly, they explain why the speed of light is always the same for all observers. Because light travels in a space-time that adjusts, that molds itself, that compensates for differences in motion. This is the core of what Einstein will send to the world in 1905. The theory of special relativity. Special because it only deals with uniform motion without acceleration. But even in its limited form, it's a revolution, because it says that the two things we believed most fundamental, most absolute, most immutable, space and time, are neither absolute nor immutable. They're flexible, malleable, dependent on the observer. There's more. If space and time are connected in this way, then so are mass and energy. Einstein derives the most famous equation in the history of science. E equals mc squared. Energy equals mass times the speed of light squared. It seems simple, almost trivial, but it's devastating in its implications. It says that mass is concentrated energy, that inside every gram of matter there's a colossal amount of energy waiting to be released. The speed of light squared is an enormous number. 300 million meters per second, multiplied by itself. That means even a small amount of mass contains a gigantic amount of energy. In 1905, this is theoretical, a mathematical curiosity. No one knows how to release that energy. No one imagines the consequences. Einstein certainly doesn't. He's solving a problem of pure physics. He's seeking logical coherence in equations. He's not thinking about bombs. He's not thinking about weapons. He's thinking about truth. But truth isn't neutral. Truth has consequences. And this particular truth will have consequences that will overshadow everything else. For now, in 1905, Einstein is just a 26-year-old man sitting in an office in Bern. He's not famous. He's not rich. He's not a university professor. He's a third-class employee at the patent office who has just solved one of the universe's greatest mysteries. And no one knows it yet. It's March. It's April. It's May. Einstein isn't only working on relativity. His mind is ablaze with ideas he's been incubating for years. It's as if a dam has broken. Everything flows at once. He writes article after article, each one revolutionary, each one enough to make any physicist famous. He writes 4 in a few months. The first deals with the photoelectric effect. It's a strange phenomenon no one has been able to explain. When light strikes certain metals, it releases electrons. But the number of electrons doesn't depend on the intensity of the light, but on its frequency. Bright light of low frequency does nothing. Dim light of high frequency releases electrons. Maxwell's equations can't explain it. But Einstein proposes something radical. Light isn't just a wave. It's also a particle. Photons they'll later be called. Small discrete packets of energy. Each photon has an energy that depends on its frequency. If the photon has enough energy, it can release an electron. If not, it doesn't matter how many photons arrive. It's like trying to break down a door. It doesn't matter how many times you hit it gently. You need a sufficiently strong blow. This idea is revolutionary because it contradicts the wave theory of light that has been accepted for decades. Thomas Young had demonstrated that light behaves like a wave. Maxwell had built all of electromagnetism on that basis. But Einstein says, it's both. Wave and particle. Depending on how you look at it. It's the birth of quantum mechanics, though it's not yet called that. It's the first crack in classical physics that will lead to a conceptual earthquake lasting decades. The second article deals with Brownian motion. It's a phenomenon observed by botanist Robert Brown in 1827. When you look at pollen suspended in water under a microscope, the particles move. Not smoothly but erratically, zigzagging, trembling. Brown couldn't explain it. Neither could other scientists. Some thought the particles were alive. But Einstein offers an elegant explanation. The pollen particles are being constantly bombarded by water molecules. The molecules are too small to see, but their collective effect is visible. Each collision pushes the pollen in a random direction. The result is that erratic dance. The importance of this article isn't just explaining Brownian motion. It's proving that atoms exist. In 1905, this is still controversial. Many respectable scientists doubt the reality of atoms. They consider them useful abstractions, mathematical fictions, but not real things. Einstein shows that if atoms are real, if molecules really bombard particles, then Brownian motion must have certain precise mathematical properties. He predicts how much the particles must move, how it depends on temperature, particle size, liquid viscosity, and his predictions can be tested. Years later, Jean Perrin will do the experiments. Einstein's predictions will be correct. Atoms are real. The third article is about special relativity. We've already discussed it. But it's worth noting something. Einstein doesn't have access to experimental data that no one else has. He hasn't made new discoveries in the laboratory. Everything he needs is already available in the scientific literature. The Michelson-Morley experiment that didn't find the ether. Maxwell's equations. Observations about the speed of light. What Einstein does is different. He takes that known data and builds a new logical structure. He reorganizes the foundations of physics not because there are new facts, but because he's found a better way to think about the old facts. The fourth article is in addition to the third. It's where he derives E equals mc squared. 3 pages. One of the shortest and most profound derivations in the history of science. Einstein shows that if an object emits energy in the form of light, its mass must decrease. Energy has mass. Or more precisely, energy and mass are two manifestations of the same thing. They're interchangeable, convertible one into the other. It's like discovering that apples and oranges aren't different fruits, but the same fruit seen from different angles. 4 articles. Written between March and September 1905. Sent to Annalen der Physik from a modest apartment at Kramgas 49, Bern. No laboratory. No research team. Just paper, pen, and a mind that doesn't accept easy answers. Historians will call 1905 the Annus Mirabilis, the miracle year. But it wasn't a miracle. It was the result of years of silent preparation, of accumulated questions, of refusing to be satisfied with incomplete explanations. Einstein didn't have a sudden epiphany. He had 1,000 small epiphanies, each building on the previous one, each refining his understanding, until finally everything crystallized in those 4 articles. Meanwhile, life continues. Einstein keeps working at the patent office. He keeps reviewing applications for mechanical and electrical devices. His colleagues don't know what he's done. His boss doesn't know. The city of Bern doesn't know. The scientific world doesn't know yet. The articles are on their way. They've been sent. But journals take months to publish. And when they finally appear in print, who will read them? Who will pay attention to an unknown patent office employee claiming that Newton was wrong about time? Einstein waits. Not with anxiety but with a strange calm. He knows he's right. Mathematical coherence is his proof. If the equations are correct, and they are, then the conclusions are inevitable. The universe has no opinions. It doesn't vote. It simply is. And he's described how it is. Mileva is tired. They've had a son, Hans Albert, in 1904. A baby who cries at night, who needs constant attention. Mileva has abandoned her own academic aspirations. She can't compete with a man in a world that barely tolerates women in science. And now she's a mother, which means her life is changing diapers, preparing meals, keeping the house in order while Albert fills notebooks with symbols she understands but that don't belong to her. There's resentment. There's sadness. There's love too, but it's a love complicated by inequality, by abandoned dreams, by the growing sense that she's the assistant in another's life rather than the protagonist of her own. Albert doesn't see it, or doesn't want to see it. He's too absorbed in his ideas. Fatherhood is abstract to him. He loves his son in theory. But in practice, it's Mileva who does all the work. Albert is present but absent. His body is in the apartment, but his mind is on imaginary trains traveling at the speed of light. The articles are published. First one, then another, then the other 2. They appear in Annalen der Physik without fanfare, without press releases, without grandiose declarations. Just journal issues accumulating in university libraries, waiting to be read. And for months nothing happens. The scientific system reacts with the speed of a glacier. Einstein's articles are dense, technical, challenging. They require concentration. They require willingness to question what everyone takes for granted. Most physicists are busy with their own research. They don't have time to seriously consider the claim that time is relative. Sounds absurd. It sounds like philosophy, not physics. And it comes from someone who isn't even in academia. Why should they take it seriously? There are exceptions. Max Planck, one of Germany's most respected physicists, reads the relativity article. He reads it twice, 3 times. Slowly, he begins to see that Einstein isn't speculating. He's deriving. Each step follows logically from the previous one. The premises are minimal. The speed of light is constant. The laws of physics are the same for all observers in uniform motion. Nothing more. And from those 2 premises, Einstein extracts an entirely new universe. Planck begins to talk about Einstein's work. He mentions it in conferences. He discusses it with colleagues. Slowly, very slowly, Einstein's name begins to circulate. But only in specialized circles. Only among physicists working in electrodynamics and optics. For the rest of the world, Einstein remains nobody. And then there's the rejection. The skepticism. The open mockery. Some older scientists consider relativity an attack on everything they've built. They've dedicated their lives to Newtonian physics. They've written textbooks. They've trained students. And now comes this unknown young man saying the foundations are wrong. That time and space aren't what we thought. It's a threat. Not just to their ideas but to their professional identity. Others simply don't understand. Einstein's thought experiments require a type of abstract thinking that isn't natural for everyone. Many physicists are accustomed to working with equipment, with measurements, with tangible data. The idea of deriving fundamental truths only with logic and algebra seems insufficient to them. They want proof. They want to see time slow down in a laboratory. But the speeds necessary to observe relativistic effects are enormous. No one can travel that fast. No one can build a clock precise enough. So how can they know if Einstein is right? And there's anti-Semitism. Not open yet, not in 1905, but present. Einstein is Jewish. In early 20th century Europe, this matters. Not always explicitly. Not always violently. But there's an undercurrent of prejudice that affects how he's perceived. Some colleagues would never say it aloud, but they feel there's something suspicious about this ambitious Jew challenging established wisdom. It's a vague resentment, difficult to name, but it filters into professional judgments. Einstein faces isolation. He's not expelled. He's not persecuted. But he's ignored, which is sometimes worse. He keeps working at the patent office. He keeps reviewing diagrams of machines. His daily life is exactly the same as before writing the articles. Same office. Same salary. Same responsibilities. It's like having climbed Everest and returning to your office job Monday morning. No one asks you about the summit. Everyone expects you to keep filing documents. There are moments of doubt. Not about the physics, Einstein is certain of the physics, but about the personal cost. He's sacrificed a traditional academic career. He's alienated his professors. He's disappointed his family. His marriage is falling apart. His son barely knows him. And for what? To write articles no one reads. To propose ideas no one accepts. It would have been easier to conform. To get a teaching position at some secondary school. To teach basic physics to teenagers. To live a quiet, respectable, forgettable life. But he can't. Not because he's ambitious. Not because he wants fame or recognition. But because the questions won't leave him alone. Once you've seen the logical structure of the universe, once you've understood that time isn't absolute, you can't unsee it. You can't pretend you don't know. Truth is demanding. Claims you. And Einstein is a voluntary slave to that truth. The years pass. 1906, 1907, 1908. Einstein publishes more articles. He refines his theory. He responds to criticisms. He clarifies confusing points. Slowly, other physicists begin to work with his ideas. Hermann Minkowski, one of his former professors at the Polytechnic, reformulates special relativity using four-dimensional geometry. 3 dimensions of space, 1 of time, united in a single structure, space-time. Einstein initially mocks this. It seems unnecessary complication to him. But with time he'll recognize that Minkowski has seen something profound. Space and time aren't just relative. They're an inseparable unity. Space-time isn't a stage where things happen. It's part of reality's very fabric. And then Einstein has another idea. Bigger, more difficult, more beautiful. It's November 1907. He's sitting at his desk at the patent office. He's thinking about gravity. Special relativity has solved many problems, but it has an obvious limitation. It only works for uniform motion. It doesn't address acceleration. And gravity is an acceleration. When you fall, you're accelerating toward Earth. Newton's laws describe this perfectly. But Newton's laws don't fit with special relativity. Newton says gravity acts instantaneously across space. If the sun disappeared, Earth would feel the change immediately. But Einstein has demonstrated that nothing can travel faster than light. So gravity can't be instantaneous. It must propagate. It must take time. But how? Einstein is looking out the window. He sees a worker on a roof. He imagines the worker falls. And suddenly, he has what he'll later describe as the happiest thought of my life. When the worker falls, he doesn't feel his own weight. He's in free fall. For him, gravity has disappeared. It's as if he were floating in empty space. He can't distinguish between falling in a gravitational field and floating far from any planet. They're physically equivalent. This is the equivalence principle. Acceleration and gravity are indistinguishable. If you're in a rocket accelerating in empty space, you'd feel exactly the same as if you were standing on a planet's surface. There's no experiment you can do inside the rocket that tells you the difference. It's like Galileo's principle of relativity, but extended. Not only is uniform motion relative, acceleration is also indistinguishable from gravity. The implications are immediate and astonishing. If gravity and acceleration are the same, and if we know that acceleration affects time through special relativity, then gravity must also affect time. A clock in a strong gravitational field must run slower than a clock in a weak gravitational field. Time on Earth's surface runs slower than time at 10 kilometers altitude. Not by much. Fractions of a second. But it's measurable. It's real. And there's more. If gravity affects time, it must also affect space. It must bend light. Imagine a light beam crossing an elevator that's accelerating. From outside, the light travels in a straight line. But from inside the elevator, the light appears to curve toward the floor. Because the elevator is accelerating upward while the light crosses. If acceleration and gravity are equivalent, then gravity must also bend light. Einstein calculates how much. He uses Newton's equations because they're all he has in 1907. The number is small, almost undetectable, but it's there. The light from a star passing near the sun must deflect slightly. It's a prediction, a testable prediction. If someone could measure the position of stars during a solar eclipse, when the sun is dark and nearby stars are visible, they could verify whether Einstein is right. But this is only the beginning. Einstein realizes he needs something deeper. Special relativity treats space-time as a flat background, like a sheet of paper. But if gravity bends light, if it affects time, then it must be bending space-time itself. Gravity isn't a force acting through space. It's a property of space. It's the curvature of space-time. It's a radical idea. Revolutionary. Beautiful. And terrifyingly difficult to convert into mathematics. Einstein needs years. Not months. Years. He starts in 1907 and doesn't finish until 1915. 8 years of intellectual struggle. Of errors. Of dead ends. Of frustrations. He needs to learn mathematics he never studied. Riemannian geometry. Tensor calculus. Concepts he didn't even know existed when he was at the Polytechnic. He asks for help from Marcel Grossman, his former classmate who's now a mathematics professor. Grossman teaches him the tools. Einstein uses them to build a new physics. His life changes during these years. In 1909, he finally leaves the patent office. He gets his first academic position at the University of Zurich. He's an associate professor. The salary is barely better than at the patent office, but it's recognition. Special relativity has begun to be accepted. Einstein is no longer an unknown. He's a promising physicist. Young, brilliant, with provocative ideas. He moves to Prague in 1911. Then back to Zurich in 1912. Finally to Berlin in 1914, where the Prussian Academy of Sciences offers him a position with no teaching obligations. He can dedicate himself completely to research. It's an extraordinary privilege. But it comes with a cost. Mileva refuses to move to Berlin. The marriage finally breaks. They separate. Einstein stays in Berlin. Mileva and the children return to Zurich. It's an emotional divorce before being legal. Einstein writes letters to his children, but the distance is more than geographical. In Berlin, Einstein is alone. Alone with his equations. World War I breaks out. Europe bleeds. Millions die in trenches. Cities are bombed. Famine spreads. But Einstein is locked in his apartment, filling pages with symbols. He's not indifferent to suffering. He signs manifestos against the war. But his mind is mostly elsewhere. He's pursuing something he feels ever closer. The problem is brutally complex. He needs equations that describe how matter and energy curve spacetime, and how that curvature affects the motion of matter and energy. It's a self-referential system. Geometry depends on matter, and matter depends on geometry. It's like trying to solve a puzzle where each piece changes shape depending on the other pieces. Einstein makes mistakes. He publishes preliminary equations that later have to be corrected. He embarks on directions that turn out to be incorrect. There are moments when he thinks he's close, only to discover he's overlooked something fundamental. It's exhausting. It's humiliating. It's the type of work that breaks most people. But in October 1915, something changes. Einstein has returned to the basic equations. He's eliminated unnecessary complications. He's simplified. And suddenly he sees the structure. He sees how everything fits. The equations are elegant. They're inevitable. They're correct. On November 25, 1915, he presents his final work to the Prussian Academy. Einstein's field equations. 10 coupled nonlinear equations that relate the curvature of spacetime to the distribution of matter and energy. They're the most beautiful equations ever written. They're the theory of general relativity. Gravity isn't a force. It's geometry. Planets don't orbit the sun because there's an invisible force pulling them. They orbit because the sun curves spacetime around it, and planets simply follow the straightest possible path in that curved space. It's like placing a bowling ball on a stretched sheet. The sheet sinks. If you now place a marble on the sheet, it will roll toward the bowling ball. Not because there's a force attracting the marble, but because the sheet's geometry is curved. The universe stops being a stage. It's an actor. Spacetime isn't passive. It responds. It curves. It stretches. It compresses. Matter tells spacetime how to curve. Spacetime tells matter how to move. It's a dance. A continuous conversation between geometry and physics. Einstein applies his new equations to the problem that has been bothering astronomers. Mercury's orbit. Mercury orbits so close to the sun that gravitational effects are stronger. Its orbit isn't a perfect ellipse. It precesses slowly. The point closest to the sun advances about 43 arc-seconds per century. Newton's equations can't fully explain this. Astronomers have proposed invisible planets, fields of matter, all kinds of ad hoc adjustments. Einstein enters Mercury's data into his equations. He calculates, and he gets 43 arc-seconds per century. Exactly. Without adjustments. Without additional assumptions. General relativity naturally predicts what Newton cannot. When he sees this result, Einstein will later say he felt as if something had broken inside him. It's the confirmation he needed. Not from others. from himself. The theory is correct. The universe works this way. He's seen the mind of God and its geometry. But the war continues. No one pays attention. Scientific journals still publish, but who has time to read about the curvature of space-time when the world is destroying itself? Einstein sends copies of his work to colleagues in neutral countries. He hopes someone somewhere will read and understand. And someone does. Arthur Eddington, a British astronomer and pacifist Quaker, receives Einstein's work through contacts in Holland. Eddington reads the equations. He studies them. He realizes Einstein has made a specific prediction. Starlight must bend when passing near the sun. And that bending must be exactly double what Einstein predicted in 1907 using Newton's equations. It's 1.75 arc-seconds. Small but measurable. Eddington also realizes this prediction can be tested. During a total solar eclipse, when the sun is dark, it's possible to photograph stars that are near the sun in the sky. If their positions are compared with positions when the sun isn't present, it should be possible to see if the light has been deflected. It's the perfect experiment. The war ends in November 1918. Europe is devastated. But science can continue. Eddington organizes 2 expeditions for the solar eclipse of May 29, 1919. One goes to Sobral, Brazil. The other to Principe Island, off the West African coast. Eddington leads the expedition to Principe. They carry photographic plates, telescopes, measuring equipment. On eclipse day, the weather is uncertain. Clouds cover the sky. Eddington waits. The eclipse begins. For a few precious minutes, the moon blocks the sun. The sky darkens. Stars appear. Eddington takes photographs. Several plates. Quickly. The eclipse ends. Light returns. It takes weeks to analyze the results. The plates must be measured with extreme care. Star positions must be compared with reference photographs taken months before. It's meticulous, tedious work. But finally the numbers emerge. Light bends. Exactly as Einstein predicted. 1.75 arc-seconds. General relativity is correct. On November 6, 1919, the Times of London publishes a headline that will change everything. Revolution in Science. New Theory of the Universe. Newtonian Ideas Overthrown. Revolution in Science. New Theory of the Universe. Newtonian Ideas Overthrown. It's not an article in a specialized journal that only other physicists will read. It's the front page of the world's most important newspaper. And the name that appears again and again is Einstein. Albert Einstein. The man from the patent office. The unknown physicist. Suddenly he's the center of global attention. The Royal Society of London organizes a joint meeting with the Royal Astronomical Society to officially announce the results of the eclipse expeditions. The hall is full. Scientists, journalists, members of the British aristocracy. There's an atmosphere of anticipation, of something historic about to happen. Sir Frank Dyson, the Astronomer Royal, presents the findings. The photographs from Sobral and Principe. The careful measurements. The numbers that match Einstein's predictions. Joseph John Thomson, president of the Royal Society and discoverer of the electron, stands up. He declares that the result is one of the greatest achievements of human thought. That Einstein has completed what Newton began. That general relativity is not only correct but beautiful. But there's something more to this celebration. Something that goes beyond pure science. It's 1919. World War I has just ended. Millions have died. Europe is in ruins. Hatred between nations is still palpable. And here is the British Royal Society, validating the work of a German scientist. Here is Arthur Eddington, an Englishman traveling around the world to prove Einstein's theory. It's a gesture of reconciliation. A reminder that science transcends borders. That knowledge has no nationality. That it's possible to work together even after the most destructive war in history. Einstein wakes up famous. Not gradually. Not in specialized circles. Immediately. Globally. Overwhelmingly famous. Newspapers around the world reproduced the story. From New York to Tokyo, from Paris to Buenos Aires, Einstein's name is everywhere. Photographers chase him. Journalists harass him with questions. They want interviews. They want explanations. They want him to translate his incomprehensible equations into something ordinary people can understand. What does it mean that space is curved? How can time go slower? Why does it matter? Einstein tries to explain. He gives lectures. He writes popular articles. He uses metaphors. He imagines space-time as a fabric, planets as balls that deform it. He talks about trains and clocks and beams of light. Some understand. Most don't. But it doesn't matter. What matters is that Einstein represents something. He's become a symbol. The solitary genius who challenged established wisdom and was right. The man who saw beyond what everyone else could see. The prophet of a new era. And he's a perfect symbol for his time. The post-war world needs heroes. It needs to believe that progress is possible. That the human mind can overcome any obstacle. That there's order in chaos. Einstein offers all that. His theory is incomprehensible to most, but that only makes it more magical. It's like a religious revelation. You don't need to fully understand it to feel it's important. Universities invite him. Governments honor him. He receives honorary doctorates from Oxford, Cambridge, Princeton, the Sorbonne. He travels to the United States. Crowds receive him like a movie star. In Japan, thousands of people fill the streets to see him pass. In Palestine, he's celebrated as a son of the Jewish people who has brought glory to his community. Einstein is uncomfortable with all this. He doesn't like the attention. He doesn't like being treated as if he were more than human. But he understands that now he has a platform. And he decides to use it. He speaks about peace. About disarmament. About the need for a world government that can prevent future wars. He becomes an activist. He signs petitions. He writes open letters. He opposes German militarism. He supports pacifism. It's controversial. Some admire him for his moral courage. Others accuse him of being naive, of meddling in politics when he should stay in his laboratory. But Einstein can't separate science from ethics. For him, both seek truth. And truth isn't neutral. But something else is happening. Something deeper than fame. Einstein's relativity is changing how humanity thinks about itself. Not just in physics, in everything. The universe stops being a clock. For centuries since Newton, we've lived in a mechanical cosmos. Predictable. Deterministic. A closed system of causes and effects where, if you know the initial conditions, you can calculate the entire future. It was a safe but suffocating universe. It left no room for the unexpected. For freedom. For mystery. And now Einstein says time isn't absolute. That simultaneity is relative. That two observers can disagree about which events occurred first and both be right. Suddenly, reality is more fluid, more ambiguous, more open, and the cultural world responds. Artists had already begun to fragment reality before Einstein. Picasso and Braque's Cubism, painting objects from multiple simultaneous perspectives, as if space could be seen from all angles at once. Marinetti's Futurism, celebrating speed and movement. But now they have scientific validation. If Einstein can demonstrate there's no absolute point of view in the universe, then there's no absolute point of view in art either. Renaissance perspective, with its single vanishing point, its fixed geometry, its clear hierarchy, becomes obsolete. Art can be multiple, fragmented, relative. Marcel Duchamp creates Nude Descending a Staircase, a painting that shows movement through time, the body decomposed into successive positions. Its direct influence from relativity. Time as the fourth dimension. Movement as an integral part of existence. Virginia Woolf writes novels where time flows non-linearly, where consciousness jumps between moments, where past and present intermingle. James Joyce experiments with language, breaking syntax, creating a stream of consciousness that reflects the relativity of subjective time. If physical time is relative, so is psychological time. Philosophers debate. Henri Bergson, the French philosopher, challenges Einstein. He says there's a difference between time measured by clocks and time lived by consciousness. La durée, he calls it. Real, qualitative duration that can't be reduced to numbers. Einstein responds that physics can only speak of measurable time, of time that affects physical phenomena. But he acknowledges there are aspects of human experience that escape equations. It's a debate that's never fully resolved, because both are right in their own terms. Relativity filters into popular culture. It becomes metaphor. It becomes slogan. Moral relativism, some say. If everything is relative in physics, why not in ethics? Einstein is horrified by this interpretation. Relativity doesn't mean anything goes. It doesn't mean there are no absolute truths. On the contrary, there are absolute truths in relativity. The speed of light is absolute. The laws of physics are absolute. What's relative is the perspective from which you observe those truths. But the truths themselves don't change. However, the confusion persists. The word relativity is too seductive, too easy to misinterpret. Einstein will later say he should have called his theory invariance instead of relativity, because that's what it's really about. Finding the things that don't change, the invariance in a universe where perspective does change. But the damage, if it is damage, is done. The 20th century enters the era of relativity. Not just scientific, but cultural, moral, aesthetic. Victorian certainty crumbles. Modernity is fluid, multiple, ambiguous. And Einstein, whether he wants it or not, is the prophet of this new vision. Universities reformulate their programs. Physics becomes more mathematical, more abstract. It's no longer enough to observe and measure. You have to think conceptually. You have to visualize spaces we can't see, dimensions we can't touch. Four-dimensional space-time. Curvature that isn't a curve in space, but of space itself. It's difficult. Many old guard physicists never fully accept it. They die believing in the ether. They die believing Newton was right and Einstein is overrated. But the new generation embraces it. Young physicists around the world study relativity. They expand it. They apply it to new problems. In the 20s, quantum mechanics emerges as another challenge to classical physics. Heisenberg, Bohr, Schrödinger, Dirac. They're building a new physics for the microscopic world. Particles that behave like waves. Probability instead of certainty. The impossibility of simultaneously knowing a particle's position and momentum. It's strange. It's disturbing. It's as radical as relativity. And Einstein doesn't like it. Ironically, the man who revolutionized physics can't accept the next revolution. He resists the probabilistic interpretation of quantum mechanics. He says his famous phrase, "God does not play dice with the universe." He believes there must be hidden variables. That the apparent randomness of quantum mechanics is only temporary ignorance. That a more complete theory will restore determinism. But most physicists disagree. And Einstein, for the first time in his life, is on the wrong side of history. Not that he's completely wrong. His objections to quantum mechanics are profound, philosophically important. But experimental evidence supports Bohr's interpretation. Nature is fundamentally probabilistic at the quantum level. Einstein never accepts it. He spends the last decades of his life searching for a unified theory that reconciles general relativity with quantum mechanics. He doesn't find it. It's the only great problem that escapes him. But let's return to 1919. To 1920, to the years when Einstein is universally celebrated, when he's the world's most famous scientist, when his face is in magazines, his name in popular songs, his image used to sell products. He becomes iconic. The wild hair, the penetrating eyes, the wrinkled sweater, the pipe. He's the archetype of the absent-minded genius, of the mad professor, of the thinker so absorbed in abstract ideas he forgets to tie his shoes. And there's truth in that image. Einstein is absent-minded. He forgets appointments. He loses letters. He dresses carelessly. He doesn't care about social conventions. But behind the icon is a man. A complicated man. Contradictory. Sometimes admirable, sometimes disappointing, completely human. His personal life is a disaster. The divorce from Mileva finally becomes official in 1919. He immediately marries his cousin Elsa, with whom he's been having a relationship for years. Elsa is the opposite of Mileva. She has no intellectual ambitions. She's practical, social, organized. She manages Einstein's growing fame. She answers correspondence. She organizes his schedule. She protects him from unwanted visitors. In a sense, she's more a manager than a wife. Einstein needs her, but it's unclear whether he loves her. And there are his children, Hans Albert and Eduard, who live with Mileva in Zurich. Einstein sees them rarely. He writes letters, sends money, but he's absent. Hans Albert resents it. He feels his father chose physics over his family. And he's right. Einstein chose. Not consciously, perhaps. Not with malice. But he chose. Einstein's mind is always on the equations. His personal relationships are abstract. He loves them in theory but can't connect emotionally. It's as if he has a finite capacity for attention and all of it is invested in understanding the universe. Nothing remains for the people closest to him. Eduard, the younger son, develops schizophrenia in his adolescence. It's devastating. Einstein doesn't know how to deal with it. He visits Eduard occasionally. He pays for his treatment. But he can't face the reality of his son's mental illness. It's too uncontrollable, too irrational. Einstein can handle the paradoxes of space-time but not those of the human brain. Eduard spends much of his life in psychiatric institutions. He dies in 1965, forgotten by almost everyone except his mother. Mileva suffers. Economically because the money Einstein sends is never enough. Emotionally because she's lost her career, her identity, her future. She becomes bitter. Sick. She spends her last years in poverty and pain. When she dies in 1948, Einstein doesn't attend the funeral. He sends a letter to his sons. It's cold, formal, as if he were writing about someone he barely knew. Is Einstein cruel? Is he selfish? Yes. But he's also a product of his time and nature. In an era when women are seen as auxiliaries to men, when fatherhood is seen as mother's responsibility, Einstein isn't exceptional in his negligence. He's typical. What's exceptional is his genius. And that genius has a price. Not just for him. For everyone around him. Fame also has a price. Einstein becomes public property. He can't walk down the street without being recognized. Strangers ask him for autographs. Children ask him for help with math homework. Journalists invent quotes he never said. His opinions on any topic are solicited and published. He speaks about education, about politics, about religion, about music. And every word is analyzed, criticized, misinterpreted. And there's anti-Semitism. As the 20s progress, the climate in Germany darkens. The economy is devastated by war reparations. Hyperinflation destroys middle-class savings. The Weimar Republic is weak, unstable. And extremists on both sides, but especially the right, seek scapegoats. Jews are the favorite target. They always have been. But now the hatred is more organized, more political, more dangerous. Einstein is an obvious target. He's Jewish. He's famous. He's internationalist. He's a pacifist. Everything German nationalists hate. There are campaigns against Jewish physics. Respectable German scientists organize conferences denouncing relativity as a Jewish conspiracy to destroy Aryan science. It's absurd. Relativity has no religion. Equations have no ethnicity. But absurdity doesn't matter when hatred seeks justifications. In 1922, Walther Rathenau, Germany's foreign minister and Einstein's friend, is assassinated by right-wing extremists. Einstein receives warnings. Death threats. Police suggest he cancel his public lectures. That he stay away from places where he could be an easy target. Einstein is frightened. He's not physically brave. He's a thinker, not a hero. He considers leaving Germany. But where to go? His fame is global, but so is anti-Semitism. He travels more. He spends less time in Berlin. He visits foreign universities. He accepts invitations from governments that want to associate with his prestige. He's received as a head of state, but always with a shadow. Always conscious that there are people who hate him not for what he said or done, but for what he is. And then, slowly, Nazism grows. First as a marginal movement, then as a political force. Hitler is a charismatic speaker who channels the rage and resentment of millions. He promises to restore German glory. He promises revenge against those who betrayed Germany. And he promises to eliminate Jewish influence. It's explicit. It's not metaphor. It's direct threat. In 1933, Hitler takes power. Einstein is in California visiting the California Institute of Technology. He reads the news. He immediately understands he can't return. Germany is no longer safe. Not even for someone as famous as him. Especially for someone as famous as him. Because his fame makes him vulnerable. A symbol the Nazis will want to destroy. He renounces his German citizenship. For the second time in his life. The first was when he was young and wanted to escape mandatory military service. Now it's for survival. The Nazis confiscate his Berlin apartment. They burn his books. They put a price on his head. 20,000 marks for information leading to his capture. Einstein never returns to Germany. The country that saw him born, where he studied, where he worked, where he developed his most important theories, has become his enemy. He settles in the United States. Princeton, New Jersey. The Institute for Advanced Study offers him a position. It's a refuge. A place where he can work without fear. But it's also exile. Einstein becomes stateless again. A citizen of the world by necessity, not by choice. Europe collapses. World War II begins. Millions die in concentration camps. Einstein's family, those who couldn't escape, among them. The 20th century, which began with such scientific hope, has become a nightmare. And in the midst of all this, Einstein's physics takes a dark turn. E equals mc squared. The equation he derived in 1905 as a theoretical curiosity. The equivalence between mass and energy. For decades it was just that. Theory. No one knew how to convert mass into energy practically. But in the 30s, physicists begin to understand the structure of the atom. The nucleus. The protons and neutrons bound by nuclear forces. And they realize something terrifying. If you can split a heavy nucleus, if you can break it, you release energy. Not a little. A monstrous amount of energy. Because the mass lost in fission converts to energy according to E equals mc squared. And C superscript 2 is enormous. In 1938, Otto Hahn and Fritz Strassmann in Germany achieve nuclear fission. They bombard uranium with neutrons. The nucleus splits. More neutrons are released. These can split more nuclei. Chain reaction. Lise Meitner and Otto Frisch, Jewish refugees working in Sweden, calculate the energy released. It's exactly what Einstein predicted. E equals mc squared isn't just theory. It's real. It's usable. It's terrifying. Because if you can create a chain reaction in a sufficiently large piece of uranium, you can release all that energy in an instant. An explosion. Not a chemical explosion like gunpowder. A nuclear explosion. Thousands of times more powerful. A single bomb that could destroy an entire city. Physicists understand the implications immediately. And they're terrified. Especially the refugees from Europe. Especially those who've escaped Nazism. Because they know German scientists have also discovered fission. And they know Hitler would have no scruples about using an atomic bomb. Suddenly, war isn't just a matter of armies and tanks. It's a race. Whoever builds the bomb first wins. Not just the war. The future. The world. Leo Szilard, a Hungarian physicist refugee in the United States, is desperate. He needs to warn the US government. He needs them to start a program to build the bomb before the Germans. But he's an unknown. No one will listen to him. He needs someone with prestige. Someone whose name opens doors. Someone like Einstein. Szilard visits Einstein in Long Island in the summer of 1939. He explains the situation. Fission. Chain reaction. The possibility of a bomb. Einstein listens. At first he doesn't fully understand the practical implications. He's a theorist, not an engineer. But Szilard is persuasive. He tells him the Germans have access to uranium mines in Czechoslovakia. That they have the scientists. That they're probably already working on it. Einstein realizes the danger. And he makes a decision that will haunt him for the rest of his life. He agrees to sign a letter to President Roosevelt. Szilard writes it. Einstein signs it. The letter is brief but urgent. It explains that uranium can be used to create extremely powerful bombs. That Germany may be working on it. That the United States must act. That it must initiate its own research program. That it must secure uranium supplies. That time is essential. The letter reaches Roosevelt in October 1939, 2 months after the start of World War II. Roosevelt reacts slowly at first. He assigns a small amount of money for preliminary research. But after Pearl Harbor, after the United States enters the war, everything changes. The program expands. Becomes massive. Ultra-secret. It's called the Manhattan Project. Thousands of scientists, engineers, technicians. Giant facilities in Los Alamos, Oak Ridge, Hanford. Led by Robert Oppenheimer. The goal? Build the atomic bomb before the Germans. Einstein doesn't participate. He has no security clearance. He's considered a political risk for his pacifist views. It's ironic. The man whose equations made the bomb possible is excluded from its construction. He works on minor projects for the war effort. Consulting on conventional explosives for the Navy. But the bomb proceeds without him. For years he doesn't know exactly what's happening. He knows there's a secret project. He knows it has to do with nuclear fission. But not the details. He doesn't know how advanced it is. He doesn't know how close they are to success. He lives in Princeton. He gives occasional classes. He works on his unified theory. He tries not to think about the war. He tries not to think about what his equation might be creating. On July 16, 1945, in the New Mexico desert, the Manhattan Project tests its device. Trinity they call it. A sphere of plutonium surrounded by conventional explosives that compress it to critical mass. The chain reaction begins. In a fraction of a second, atoms split. Neutrons fly. More atoms split. Mass converts to energy. E equals mc squared manifests as a fireball that grows, that rises, that forms a giant mushroom in the desert sky. The light is brighter than 1,000 suns. The heat melts sand into green glass. The shock wave is felt hundreds of kilometers away. Oppenheimer observes. He'll later say he thought of a line from the Bhagavad Gita. Now I am become death, the destroyer of worlds. Other scientists celebrate. They've achieved the impossible. They've released the energy of the atom. They've built a weapon that will change history. But they're also afraid. Because now that it exists, now that they know it's possible, the world will never be the same. Einstein isn't there. He's in Princeton. He learns about Trinity weeks later. Not through official channels. Through rumors. Through vague mentions and conversations. He doesn't know the details. Not yet. But he knows enough to be worried. In August, the United States is ready to use the bomb. Germany has already surrendered. Hitler is dead. The Nazi threat has been eliminated. But the war continues with Japan. Japan refuses to surrender unconditionally. The battles are brutal. Okinawa. Iwo Jima. Thousands of Americans die. Millions of Japanese. The military staff estimates that an invasion of the Japanese mainland would cost 1 million American lives. Maybe more. President Truman, who succeeded Roosevelt after his death, faces a decision. Use the bomb and force quick surrender. Or continue the war conventionally with an immense human cost. For Truman, it's not a difficult decision. He'll use the bomb. He'll end the war. He'll save American lives. Japanese lives are secondary. On August 6, 1945, a B-29 bomber called Enola Gay takes off from Tinian Island. In its hold it carries a uranium bomb. They call it Little Boy. The Little Boy. Innocent names for objects of death. The target is Hiroshima, a city in western Japan. 300,000 people live there. It's a military center, they say. A naval base. War production facilities. But it's also a city. With families. Children. Elderly. People who didn't decide the war but who will die for it. At 8:15 in the morning local time, Little Boy falls. It explodes at 600 meters above the city center. The fireball reaches several thousand degrees. It vaporizes everything within a kilometer radius. People disappear. Buildings disintegrate. The wind tears clothes off people farther away. It burns skin. Invisible radiation penetrates bodies. It alters DNA. It initiates cancers that will kill years later. The atomic mushroom rises. It's visible from 150 kilometers. The city burns. 70,000 people die instantly. Another 70,000 will die in the following days, weeks, months. Injuries. Radiation. Collapse of medical infrastructure. It's hell. Not a battle. An annihilation. 3 days later, another bomb. Nagasaki. This one plutonium. More powerful. 40,000 immediate deaths. More afterward. Japan surrenders. The war ends. The world celebrates. But it also trembles. Because everyone understands that something has changed. That now there exists a weapon that can destroy entire cities in seconds. That can kill hundreds of thousands without even fighting. That can, if used sufficiently, end civilization. Einstein is at his summer house in Long Island when he hears the news about Hiroshima. His assistant Helen Dukas tells him. Einstein says a single word. Oh ouais. Oh no. Oh pain. He sits down. He's silent. He doesn't eat. He doesn't speak. He's processing. Trying to understand what he's done. Not physically. He didn't build the bomb. But intellectually. His equation. E equals mc squared. The equivalence of mass and energy. The theoretical basis without which the bomb wouldn't exist. In the following days he speaks with journalists. He says he regrets having signed the letter to Roosevelt. He says if he had known the Germans wouldn't achieve the bomb, he would never have done anything. He says the atomic bomb has changed everything except our way of thinking, and that's why we're heading toward an unprecedented catastrophe. He says we need a world government. We need to abolish war. We need to put atomic energy under international control. Otherwise we'll destroy ourselves. He's sincere. He's horrified. But he's also in part rationalizing. Because the uncomfortable truth is that his signature on that letter helped initiate the program that created the bomb. That without his prestige, without his name, maybe the Manhattan Project would have taken longer to begin. Or never existed. It's impossible to know. But Einstein feels it. The guilt. The weight. He spends the last 10 years of his life warning about nuclear danger. He writes articles. He gives speeches. He joins peace movements. But his voice is one among millions. And the world doesn't listen. The Cold War begins. The United States and the Soviet Union accumulate nuclear arsenals. Thousands of bombs. Each more powerful than those of Hiroshima and Nagasaki. Hydrogen bombs. Fusion bombs. E equals mc squared applied on ever larger scales. The capacity to destroy the entire planet several times over. Einstein sees all this. And he despairs. He spent his life seeking truth. Believing that knowledge is inherently good. That understanding the universe is humanity's greatest achievement. But now he sees the dark side of knowledge. He sees that truth can be used for evil. That E equals mc squared can illuminate cities or incinerate them. That the same equation explaining stars can create weapons of apocalypse. In 1955, shortly before his death, Einstein signs a manifesto along with Bertrand Russell. The Russell-Einstein Manifesto. It calls on the world's scientists to unite against nuclear weapons. It warns that nuclear conflict would mean the end of humanity. It requests peaceful resolution of disputes. It's his last public act, his last warning. He dies on April 18, 1955. An aortic aneurysm. He refuses to be operated on. He says he's lived enough, that it's time to go. He dies in Princeton Hospital. His last words are in German. The nurse doesn't understand them. They're lost forever. His brain is extracted without permission and studied. As if genius could be found in tissue folds. The world mourns. Obituaries are published in all newspapers. He's erected as one of history's greatest scientists, comparable to Newton, to Galileo. And it's true. He changed our understanding of the universe more profoundly than anyone in centuries. But he also left an ambiguous legacy. Relativity, the beauty of equations, the elegance of curved spacetime, and the bomb, the atomic mushroom, knowledge that destroys. Einstein spent his life chasing light, literally and metaphorically, understanding how it travels, how it behaves, how it defines the universe's limits. But in doing so, he also unleashed shadow, a shadow that still covers us. Because every time a physicist works on nuclear fusion, every time an engineer designs a reactor, every time a politician considers the atomic arsenal, they're standing on Einstein's shoulders, using his knowledge, for good or ill. Hiroshima, August 6, 1945. 8:15 in the morning. The sky is clear. It's a perfect day. One of those days when summer light falls gently over rooftops, when mothers prepare breakfast, when children play in the streets before the heat becomes unbearable. The city awakens slowly. There are streetcars crossing bridges, office workers walking to their jobs, vendors opening their stalls at the market. 300,000 lives intertwined in the ordinary routine of existing. And then, in an instant briefer than a blink, the world changes. The bomb makes no sound as it falls. It gives no warning. It's just a dark object falling from 9,000 meters altitude, a metal cylinder 3 meters long containing 64 kilograms of uranium-235. Inside the device, designed with obsessive precision, there's a simple and brutal mechanism. A uranium projectile will be fired at another piece of uranium. When they unite, they'll reach critical mass. And then it will begin. At 600 meters above central Hiroshima, in the open air above the Aioi Bridge, the two pieces of uranium meet. Neutrons begin to fly. A uranium-235 nucleus splits. It releases energy and more neutrons. Those neutrons strike other nuclei. They split. They release more energy, more neutrons. In an infinitesimal fraction of a second, less than a microsecond, the chain reaction completes. Mass converts to energy. E equals mc squared. Not as an abstract equation on a blackboard. As devastating physical reality. The temperature at the explosion's center reaches several million degrees. Hotter than the sun's surface. The light emitted is so intense that people who look directly are instantly blinded. The radiation, invisible but lethal, travels at the speed of light. Gamma and X-rays that penetrate everything. They alter DNA. They kill cells. They destroy the body from within. Within a 500-meter radius of the hypocenter, everything that exists ceases to exist. People aren't burned. They're vaporized. Converted to gas, to plasma. They disappear so completely they leave no bodies. Only shadows. Human shadows etched into concrete walls where they stood. Permanent silhouettes of people who no longer are. A man climbing stairs. A woman sitting on a bench. A child with arms extended. Their shadows remain because their bodies blocked the radiation for a fraction of a second before evaporating. It's the most ghostly echo of human existence ever created. The fireball expands. 200 meters in diameter. 300. 500. Everything it touches incinerates. Wooden buildings ignite instantly. Not like normal fire that grows and spreads. They simply burst into flames, every board, every beam, every window exploding simultaneously. Concrete structures near the hypocenter melt. Concrete melts. like wax. Roof tiles fuse. Metal vaporizes. Glass becomes liquid drops that fall like burning rain. And then comes the shockwave. A wall of compressed air traveling at more than 1,000 kilometers per hour. An invisible tsunami that sweeps the city. It crushes everything in its path. People a kilometer from the hypocenter are lifted and thrown like dolls. Buildings collapse. They don't fall. They explode outward, their walls ripped from foundations, their beams twisted like wire. Trees are uprooted. Bridges bend. Streetcars are overturned and crushed. People who weren't vaporized, who weren't close enough to die instantly, die in other ways. Crushed under rubble. Burned by fires now consuming the entire city. Their lungs burst by overpressure. But the worst are those who survive the first minutes. Those who are far enough not to die immediately but close enough to receive massive radiation doses. They walk like zombies. Their skin hangs in strips from their bodies. Third-degree burns covering arms, legs, faces. Eyes swollen shut. Hands extended before them because the pain is unbearable when arms hang. They seek water. They cry for water. Hiroshima's rivers fill with bodies, people who crawled to the water seeking relief and died there, floating among debris. Those farther away, outside the immediate destruction radius, see the mushroom. A column of smoke and fire that rises kilometers into the sky. It expands at the top, forming that distinctive shape. The symbol of the nuclear age. The visual reminder that humans have learned to harness the forces that power stars. And they've used them to kill. The radiation does its silent work. People who seemed unharmed begin falling ill days later. Nausea, vomiting, hair loss, hemorrhaging. Their immune systems collapse. Their bone marrow stops producing blood cells. They die slowly, painfully, without anyone understanding why. Japanese doctors have never seen anything like this. They don't know they're treating radiation sickness. They don't know there's no cure. They can only watch as their patients waste away. 70,000 dead on the first day. Another 70,000 in the following months. But numbers don't capture the horror. They don't capture the mother searching through ruins for her children and finding only ashes. The father carrying his daughter's charred body, walking aimlessly because there's no hospital, no help, nothing. The 6-year-old boy sitting alone amid destruction, staring into emptiness, mute from trauma. Entire families eliminated. Stories interrupted. Lives that will never be lived. 3 days later, Nagasaki. Another bomb. This one plutonium, not uranium. More efficient. More powerful. 40,000 immediate deaths. The city is in a valley, surrounded by hills, which contains part of the explosion. Otherwise the death toll would have been higher. It's grotesque luck. As if there are degrees of catastrophe. As if it matters whether 40,000 or 100,000 die when each number represents a universe of suffering. The world learns. Images arrive slowly. Blurred photographs of atomic mushrooms. Then, later, photos of devastation. Cities converted to wastelands. Buildings reduced to twisted frames. And the survivors. The hibakusha they'll be called. The bomb people. With their keloid scars, raised and shiny tissue marking where skin was burned. With their horror stories that many will refuse to believe because they're too extreme, too inhuman. Journalists write in almost religious language. They speak of the power of the atom, as if it were a deity. They speak of harnessing cosmic forces. But they avoid describing charred bodies. They avoid talking about children dying of leukemia. The official narrative is triumph. The United States has ended the war. It has saved American lives. The bomb was necessary. It was justified. It was inevitable. But there are dissenting voices. Manhattan Project scientists who are horrified by what they've created. Not all. Some celebrate. Some think Japan deserved this for Pearl Harbor, for atrocities in China, for refusing to surrender. But others can't reconcile technical pride in having solved physics's most difficult problem with knowledge of what that achievement means in human flesh. Albert Einstein weeps. Not publicly. He's too private, too controlled for that. But in his study in Princeton, sitting in his favorite chair with his pipe unlit in his hand, he weeps. Tears roll down his cheeks and he doesn't wipe them. He lets them fall. Helen Dukas, his secretary, finds him like this. She says nothing. There's nothing to say. She sits silently beside him. Two people in a room contemplating the end of innocence. Because that's what Hiroshima represents. The end of innocence. Not just Einstein's, though certainly his, but of science itself. For centuries, science has been seen as unequivocal progress. Every discovery is good. Every advance improves human life. Electricity, antibiotics, airplanes, vaccines. Science saves lives. It makes life easier, longer, richer. But now science has created something that can end all life. Not metaphorically. Literally. If enough bombs are built, if they're used in total war, they can destroy civilization. They can make the planet uninhabitable. And guilt cannot be evaded. Scientists can't say they were only seeking truth. That applications of their work aren't their responsibility. Because many of them worked explicitly on the bomb. They calculated critical values. They designed detonation mechanisms. They solved engineering problems. They did it for good reasons. To stop Hitler. To end the war. But good intentions don't change the outcome. Hiroshima's people are equally dead. Einstein faces this reality every day during the last 10 years of his life. He wakes each morning in his modest house on Mercer Street, Princeton. He has breakfast. He reads newspapers. And every news item about nuclear weapons is a reminder. Every article about the Cold War is an accusation. His equation. E equals mc squared. The theoretical basis for everything. Without it, without understanding that mass can convert to energy, the bomb wouldn't exist. He's responsible. Not legally. Not criminally. But morally, spiritually, intellectually. Not everyone agrees. Many tell him it's not his fault. That science is neutral. That he didn't build the bomb. That he only signed a letter. That without him, someone else would have discovered relativity eventually. That scientific progress is inevitable. That you can't stop knowledge. All these things are true. And none of them console him. Because Einstein understands something many don't want to admit. That knowledge isn't neutral. That knowing how the universe works is power. And power can be used for good or evil. There's no way to separate pure knowledge from its applications. There's no way to discover truth without also discovering how that truth can destroy. It's modern science's central paradox. We seek to understand because understanding is beautiful. Because curiosity is human. Because we want to know how the universe works. But every time we understand something profound, every time we penetrate another level of reality, we gain power. And that power can be used to create or to destroy. Nuclear energy can power cities or incinerate them. Biotechnology can cure diseases or create plagues. Artificial intelligence can solve impossible problems or create autonomous weapons. Knowledge always cuts both ways. Einstein becomes an activist. He hadn't planned this role. He's a theorist, not a politician. He prefers equations to speeches. But he feels obligation. If his work contributed to the problem, then he must contribute to the solution. And the solution, he believes, is stopping nuclear proliferation. Eliminating atomic weapons before they eliminate humanity. He writes articles. He publishes essays in popular magazines. He speaks on radio. His message is consistent. Nationalism is obsolete. In the nuclear age, wars between nations mean mutual suicide. We need to think globally. We need a world government with real authority. We need to put all nuclear weapons under international control. Inspections. Transparency. Binding treaties. It's the only way to avoid catastrophe. It's a radical message for the 40s and 50s. The United States and Soviet Union are entering the Cold War. Communism versus capitalism. Democracy versus totalitarianism. Each side sees itself as civilization's guardian. Each side accumulates weapons. Atomic bombs. Then hydrogen bombs, 1,000 times more powerful. launch systems, strategic bombers. Eventually, intercontinental ballistic missiles that can cross the world in 30 minutes. The doctrine of mutual assured destruction emerges. Mad appropriately. If either side attacks, the other will respond. Both will be destroyed. Therefore, no one will attack. It's twisted logic that depends on both sides being perfectly rational, on there being no errors, no misunderstandings. It's peace maintained by terror. And to Einstein it seems insane. He speaks against this. He says we can't base our survival on the balance of terror. That eventually something will go wrong. An error. A misunderstanding. An irrational leader. And then everything will end. There will be no winners. No second chance. Only extinction. But his voice is a minority. In the United States, during the McCarthy era, speaking of international cooperation is suspicious. It's almost treason. Einstein is investigated by the FBI. J. Edgar Hoover maintains a file on him. They consider him a communist sympathizer. It's absurd. Einstein isn't a communist. He's a humanist. He believes in individual freedom, in critical thinking, in human dignity. But he also believes in social justice, in workers' rights, in the need to regulate capitalism. These opinions make him dangerous in Cold War America. He loses friends. Scientific colleagues who think he should stay silent. That he should leave politics to politicians. That he's damaging his reputation. Einstein doesn't stop. He says intellectuals have a responsibility to speak. That silence is complicity. That if scientists don't warn about dangers of their own work, no one else will. He defends Julius and Ethel Rosenberg, executed for atomic espionage. Not because he believes they're innocent, though he doubts the evidence, but because he opposes the death penalty. Because he believes anti-communist hysteria is destroying civil liberties. He signs petitions. He writes letters to the president. It's useless. The Rosenbergs are executed. The arms race continues. The world divides ever more into hostile blocs. Einstein also speaks about education, about freedom of thought, about the danger of mixing science with nationalism. He says universities must be places of free questioning, not indoctrination. That students must learn to think, not what to think. That education's purpose is creating individuals who can judge critically, not masses who obey orders. It's a direct critique of the system that formed him. German authoritarianism. But also of tendencies he sees in America. Conformism. Fear of dissent. Pressure to support government policies without questioning. Einstein says this betrays the scientific spirit. That science progresses through disagreement, through questioning, through willingness to challenge orthodoxy. A society that demands conformity is a society that stops advancing. He also speaks of racism. Einstein is part of the NAACP. He supports the civil rights movement. He's experienced discrimination as a Jew. He understands irrational hatred. In the United States, he sees segregation and recognizes it as the same evil. He says racism is a disease of white people, that it must be confronted and eliminated. These declarations make him even more controversial in 1950s America. Einstein's image during this final decade is complex. Publicly, he remains the genius, the world's most famous scientist. His face is iconic. The disheveled white hair, the penetrating eyes, the wrinkled sweater. He's science's grandfather. Wise, kind. But he's also seen as politically naive, as an idealist disconnected from reality. The realists, the decision-makers, military strategists, and diplomats ignore him. They respect his science, but they consider his political opinions irrelevant. Einstein feels the frustration. He spent his life solving problems, finding elegant solutions to complex questions. But this problem, the problem of how to avoid nuclear annihilation, can't be solved with equations. It requires changing human nature. It requires people to overcome tribalism, nationalism, fear of the other. It requires an evolutionary leap in consciousness. And Einstein doesn't know how to make that happen. He works until the end. Not in politics, there he feels powerless. But in physics, his last obsession is the unified theory. The dream of combining general relativity with quantum mechanics. Of finding one equation, one master theory that explains everything. Gravity, electromagnetism, nuclear forces, all as manifestations of a single principle. He fills notebooks with calculations. He tries different approaches. All fail. The problem is too difficult. It requires mathematics that don't yet exist. It requires concepts that haven't yet been imagined. Einstein is working at the frontier of the knowable. And this time the frontier doesn't yield. His younger colleagues think he's wasting time. That the unified theory is impossible. Or at least premature. That we need to better understand quantum mechanics first. That Einstein is chasing a dream. But he can't stop. It's his nature. Always seeking underlying order. Always believing the universe is comprehensible. That there's a deep logic waiting to be discovered. He doesn't find it. He dies without completing his theory. His last pages of calculations are on his nightstand in the hospital. Unfinished equations. Unsolved problems. It's appropriate in a way, because science never ends. Every answer generates new questions. Every discovery opens new mysteries. Einstein dies knowing this. Knowing his work will continue without him. That others will take his ideas and carry them further. That the search for truth is infinite. And that consoles him more than any individual achievement. Because it means human curiosity, the impulse to understand, will survive. Even if we create bombs. Even if we kill each other. As long as there are humans, there will be questions. And as long as there are questions, there's hope. Einstein's legacy unfolds slowly in the decades after his death. In the 60s, general relativity, which had been seen as beautiful but academic, becomes central to cosmology. Astronomers discover objects that can only be explained by Einstein's physics. Quasars, pulsars, and finally indirect evidence of black holes. Black holes are perhaps general relativity's strangest prediction. Einstein himself didn't believe they existed. They're regions where space-time curvature becomes infinite. Where gravity is so strong that nothing, not even light, can escape. Time stops at the event horizon. Space collapses to a point of infinite density. It's mathematically correct, but seemed physically impossible. But in 1967, John Wheeler coins the term black hole, and astronomers begin searching seriously. They find stellar systems where a visible star orbits something invisible. Something massive. Something that emits X-rays when matter falls toward it. The only explanation, a black hole. A star that has collapsed so completely it has disappeared from the observable universe, leaving only its gravity. In 1971, the first strong candidate is identified, Cygnus X1. Then more. Dozens. Hundreds. At the center of most galaxies, including ours, there are supermassive black holes. Millions, even billions of times the sun's mass. These gravitational beasts control galaxy evolution. They're cosmic engines accreting matter, emitting energy jets extending for light years. All predicted by Einstein's equations. Equations written in 1915, when the idea that stars could collapse into singularities was pure fantasy. But mathematics doesn't lie. If the equations are correct, and they are, then black holes must exist. And they do. In 2015, exactly 100 years after Einstein completed general relativity, the LIGO collaboration detects gravitational waves. Another Einstein prediction. If spacetime can curve, it can also ripple. Like throwing a stone in a pond, but the pond is the universe's structure. Cataclysmic events like two black holes colliding send waves through spacetime. Those waves stretch and compress space as they pass. Einstein calculated this in 1916. He even derived equations for gravitational waves. But he thought they'd be too weak to detect. He was right that they're weak. Incredibly weak. LIGO had to build detectors 4 kilometers long that can measure distance changes smaller than a proton's width. It's technology Einstein couldn't imagine. But it works. And in September 2015, two black holes colliding a billion light-years away produced a wave LIGO detected. Space-time literally rang like a bell. And we heard it. Since then, dozens more detections. Black hole collisions. Neutron star collisions. Each confirming general relativity with astonishing precision. Each showing that Einstein saw deeper into reality's structure than any of his contemporaries. But relativity isn't just exotic science. It's everyday technology. Every smartphone, every GPS navigator depends on Einstein's relativity. GPS satellites orbit at 20,000 kilometers altitude. They move fast. Special relativity predicts their clocks run slower than clocks on Earth by about 7 microseconds per day due to their velocity. But general relativity predicts their clocks run faster by 45 microseconds per day because they're in a weaker gravitational field. The net effect is 38 microseconds per day faster. If we didn't correct for this, GPS would accumulate errors of 10 kilometers per day. It would be useless, but we correct. Clocks and satellites are adjusted to compensate for relativistic effects. And it works perfectly. Every time you use your phone to navigate, you're using Einstein's relativity. You're trusting that time runs differently depending on how fast you move and how deep you are in a gravitational field. Modern cosmology is unthinkable without Einstein. In 1929, Edwin Hubble discovered the universe is expanding. Galaxies are moving away from each other. The farther they are, the faster they move. The only explanation, the universe itself is expanding. Space between galaxies is growing. If the universe is expanding now, then in the past it was smaller, denser, hotter. Go back far enough in time and the entire universe was compressed in a point of infinite density. The Big Bang. Not an explosion in space, but an explosion of space. The universe's origin itself. This idea is direct application of general relativity. Einstein's equations allow a dynamic universe. A universe that can expand or contract. Einstein initially didn't like this. He added a cosmological constant to his equations to make the universe static. He later called it his greatest blunder when Hubble discovered expansion. But ironically, the cosmological constant has returned. In the 90s, astronomers discovered the universe's expansion is accelerating. Something is pushing galaxies apart. They call it dark energy. And it's mathematically identical to Einstein's cosmological constant. The blunder that wasn't a blunder. General relativity also predicts the universe's extreme past. In the first moments after the Big Bang, the universe was so hot and dense that physics becomes strange. Matter and antimatter annihilating. Particles creating from vacuum. The four fundamental forces unified in one. It's territory where general relativity and quantum mechanics must merge. And we still don't fully know how to do that. It's the problem Einstein couldn't solve. The problem of the unified theory. And it remains physics's greatest challenge. But there's progress. String theory proposes fundamental particles aren't points, but tiny vibrating strings. Different vibration modes correspond to different particles. It's elegant. It's mathematically rich. It naturally unifies all forces. But it also predicts extra dimensions, parallel universes, and things we can't test experimentally. At least not with current technology. It's controversial. Some physicists believe it's the path to the final theory. Others think it's philosophy, not science. Loop quantum gravity is another approach. It proposes space-time itself is quantized. It's not a smooth continuum but a foam of tiny loops at the Planck scale. It's different from string theory. More conservative in some senses. More radical in others. Also without clear experimental confirmation. These are Einstein's thoughts heirs. Physicists trying to complete what he began. To find the final theory. The equation that explains everything. We don't know if such a theory exists. Perhaps the universe is fundamentally irreducible. Perhaps there will always be another level of depth. Another unanswered question. But the search continues. Stephen Hawking dedicated his life to understanding black holes. He showed black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. Hawking radiation. It's tiny, undetectable with current technology, but it's real. And it means black holes eventually evaporate. A sun-sized black hole would take 10 to the power of 67 years to evaporate, much longer than the universe's current age. But eventually it will happen. Everything decays. Everything has an end. Hawking also worked in cosmology. With Roger Penrose, he proved that if general relativity is correct, the Big Bang was inevitable. There's no way to avoid the initial singularity using only general relativity, which means either general relativity is incomplete, or the universe really began from a point of infinite density. It's a profound result. A mathematical theorem about the universe's origin. Kip Thorne explored general relativity's extreme possibilities. Wormholes, time travel, space-time warping. Most is speculation. But it's speculation informed by rigorous mathematics. Einstein's equations permit these things in principle. Whether we can build them is another question. Probably not. It would require exotic matter with properties we've never observed. Negative energy, negative mass. But the equations don't absolutely prohibit them. And that's fascinating. The Event Horizon Telescope collaboration photographed a black hole in 2019. Not directly. You can't photograph something that doesn't emit light. But you can photograph the shadow. The bright accretion disk surrounding the black hole, with a dark region at the center where light is absorbed. The black hole at Galaxy M87's center. 6.5 billion times the sun's mass. 55 million light-years away. And there it is. Exactly as Einstein's equations predict. A ring of light warped by extreme spacetime curvature. A black hole's shadow. These discoveries aren't just Einstein confirmations. They're expansions of his vision. Each reveals something new about the universe. Each raises new questions. What happens inside a black hole? Does spacetime really become infinite at the center? Or is there something more our current physics doesn't capture? What is dark energy? Why does the universe accelerate? What is dark matter that constitutes 85% of matter but we've never directly detected? Einstein didn't answer these questions. But he created the framework where they can be formulated. Before relativity, we had no language to speak about spacetime curvature. We had no way to conceptualize a dynamic universe. We were trapped in the Newtonian paradigm. Einstein freed us. He showed us the universe is stranger, richer, more beautiful than we thought. And his influence goes beyond physics. The idea that space and time are relative, that there's no absolute reference frame, has permeated culture. Philosophers have discussed implications for free will, for causality, for reality's nature. Artists have explored multiple perspectives: temporal fragmentation, subjective realities. Science fiction writers have imagined faster-than-light travel, time paradoxes, parallel universes. Not all of this is physically correct. Most isn't. But it's inspired by Einstein, by the idea that the universe isn't what it seems. That deep truths are counterintuitive. That common sense is insufficient to understand reality. That we need mathematics, rigorous logic, willingness to abandon prejudices. In education, Einstein has become a symbol. The rebel genius. The one who questioned authority. The one who thought differently. There's truth in this, but also mythology. Einstein didn't succeed despite questioning authority. He succeeded because he was right. Schools sometimes use Einstein to justify not teaching fundamentals. Einstein failed math, they say. It's false. Einstein was excellent at mathematics. What he failed was the Polytechnic entrance exam because he hadn't completed his secondary education in non-scientific areas. The lesson isn't that you can ignore formal education. It's that formal education must foster creativity alongside knowledge. Einstein's image, the icon, has been commercialized. His face on t-shirts, posters, mugs. The tongue out in that famous 1951 photograph. He's become a brand. Representing genius, creativity, eccentricity. Tech companies use it to seem innovative. universities to seem prestigious. It's reductionism. Einstein was more complex than the icon, more human, more fallible. But perhaps the icon serves a purpose, reminding us that humans can understand the universe, that the mind, that 3-pound thing of neural tissue, can comprehend laws governing galaxies, that we can imagine dimensions we can't see, that we can calculate the cosmos's fate. It's extraordinary. And if Einstein could do it, if a patent office employee in Bern could rewrite physics, then perhaps others can too. Perhaps you can. Perhaps I can. That's the inspirational legacy. But there's another legacy. Darker. The bomb. Knowledge that destroys. Einstein spent his last years trying to put that genie back in the bottle. He couldn't. Nuclear weapons still exist. Thousands of them. Enough to destroy civilization many times over. We've avoided nuclear holocaust for 75 years. Not because we're wise, but because we've been lucky. Because errors haven't escalated. Because leaders so far have been rational enough. But the threat remains. And not just from weapons. Nuclear fusion, the power that feeds the sun, could be unlimited clean energy. But it could also be more powerful hydrogen bombs. CRISPR can cure genetic diseases. It can also create engineered pathogens. Artificial intelligence can solve impossible problems. It can also create autonomous weapons systems. Every powerful technology has this dual character. We can't have one without the possibility of the other. Einstein understood this viscerally. And he had no answer. Only warnings. Imagination gave us wings, he said, but power wants to use those wings as weapons. We need wisdom to match our knowledge. We need ethics to guide our technology. We need to think about consequences before acting. But how? How do we create that wisdom? How do we teach ethics in a world where success is measured in money and power? How do we convince people to cooperate when tribalism is instinctive? These questions remain unanswered. 70 years after Einstein's death, we're still struggling with them. Perhaps we'll never fully resolve them. Perhaps the human condition is always walking this tightrope between genius and destruction. Perhaps the best we can do is stay conscious of danger. Stay vigilant. Stay hopeful that wisdom will eventually catch up to knowledge. Einstein would have wanted that. Not certainty. Not final solutions. But continuous struggle. Continuous questioning. Continuous improvement. Because that's what science is at its best. Not dogma. Not absolute truths carved in stone. But increasingly better approximations. Increasingly accurate models. Increasingly deeper understanding. It's a process, not a destination. And the process, if we do it right, brings us closer to truth. But we never arrive. There's always more to discover. There's always another question. And that, paradoxically, is what makes the search worthwhile. There's a photograph, the most famous of all. Einstein on his 72nd birthday, leaving a party in Princeton. Photographers surround him. Flash after flash. He smiles politely, tired. He spent days answering banal questions. What does it feel like to be 72? What's the secret of happiness? Whether he believes in God. The same questions always. As if his age mattered. As if happiness had a formula. As if God were a mathematical problem. Arthur Sass, photographer for United Press International, asks him for one more smile. One last photo. Einstein is fed up. He's smiled all night. He's posed. He's been kind. But at that moment something breaks. The exhaustion. The frustration of being treated as an object rather than a person. The absurdity of the whole situation. And then instead of smiling he sticks out his tongue. A childish gesture. Irreverent. Totally unexpected from a 72-year-old man, a professor emeritus, the world's most famous scientist. Sass captures the moment. The click of the shutter. And that image becomes iconic. Not Einstein the scientist. Not Einstein the genius. But Einstein the human. Playfully rebellious. Refusing to be what's expected of him. It's perfect precisely because it breaks the image. because it shows that behind the myth there's a man who gets tired, who gets frustrated, who has a sense of humor. Einstein loves that photograph. When Sass sends him a copy, Einstein crops it, removing the other people in the car, leaving only his face with tongue out. He makes copies. He sends them to friends as New Year's cards. It's his way of saying, "Don't take me too seriously. I'm just a person. Stubborn. Absent-minded. Sometimes childish. Not a god. Not an oracle. Just a man who spent his life asking questions. But the world doesn't listen. Or rather, the world listens selectively. It takes the image and converts it into something different. Mad genius. Crazy professor. The archetype of the eccentric scientist. It becomes merchandise. Posters in college dorms. T-shirts. Internet memes decades later. The irony is cruel. Einstein used that photo to humanize himself. The world uses it to turn him into caricature. And that's the central tension of Einstein's posthumous existence. The distance between man and myth. Between who he really was and what he represents now. The Einstein myth is simple. Genius. Revolutionary. The man who saw what no one else could see. Who defied orthodoxy and was right. The victorious rebel. It's a clean narrative. Inspirational. Easy to sell. The Einstein man is complicated. He was brilliant, yes. Perhaps the most original physicist of the 20th century. But he was also stubborn to the point of arrogance. He rejected quantum mechanics not for solid scientific reasons but for philosophical preference. He didn't like indeterminacy. He didn't like probability. He wanted a deterministic universe where, if you knew all variables, you could predict the entire future. It's an understandable position. But he was wrong. And he spent the last 3 decades of his life pursuing a unified theory that never worked, using methods his colleagues considered obsolete. He was a bad husband. Twice. With Mileva, he was emotionally absent, obsessively focused on his work, unable to connect when she needed him most. The divorce was brutal. Einstein wrote a list of conditions Mileva had to accept if she wanted to remain married. She couldn't expect physical intimacy. She couldn't expect him to sit with her or go out with her. She had to serve meals in his room. She had to clean his clothes. She had to leave immediately if he asked. It's a horrible document. It treats Mileva as a servant, not a wife. She accepted for a time, desperate to keep the family together. But eventually she couldn't anymore. The marriage ended. Einstein felt relieved. With Elsa it was different but not necessarily better. She didn't expect intellectual intimacy. She didn't compete with his work. She managed the practical aspects of his life. Correspondence, schedule, visitors. She was a manager more than a companion. And Einstein was fine with that. But he also had affairs. Multiple. With secretaries, students, acquaintances. Elsa knew. She suffered in silence. The tacit agreement was that she got the status of being Einstein's wife. He got freedom. It's a cynical arrangement. Very much of its era, perhaps. But not admirable. He was a bad father. Hans Albert, his eldest son, wrote later about the emotional distance. How Einstein could be in the same room but completely absent, lost in thought. How visits were formulaic, obligatory. How Einstein seemed more comfortable writing letters than speaking face-to-face. Edouard, the younger son who developed schizophrenia, was virtually abandoned. Einstein visited occasionally. He paid medical bills. But he couldn't or wouldn't face the reality of his son's mental deterioration. It was too chaotic. Too irrational. Einstein needed order. Edouard's illness was the antithesis of order. He could also be arrogant. In scientific debates, he sometimes dismissed contrary opinions without proper consideration. When Werner Heisenberg presented the uncertainty principle, Einstein devised thought experiments to refute it. All failed. Niels Bohr dismantled them one by one. But Einstein didn't give up. Not because he had new evidence, but because he couldn't accept that the universe worked that way. Eventually, even his closest friends became frustrated. Paul Ehrenfest wrote to him, "Einstein, you shame yourself. You sound exactly like relativity's opponents. These aren't the characteristics of myth. The myth has no flaws. The myth is heroic. But the man had all normal human flaws. Selfishness. Insecurity disguised as confidence. Emotional incapacity. Stubbornness. What makes him interesting isn't that he was perfect. It's that despite his flaws, he achieved something extraordinary. Not by being superhuman. By being exactly human. With obsessions. With monomania. With the capacity to focus so intensely on a problem that everything else disappears. The narrative voice must become intimate here. Personal. As if we're looking at family photos. Private notebooks. Letters never meant to be published. Einstein the icon is two-dimensional. Einstein the man is three-dimensional. Contradictory. Sometimes admirable. Sometimes disappointing. Always human. He went days without bathing. His famous hair was disheveled not by style but by neglect. He simply didn't care. He stopped wearing socks because they developed holes and it seemed pointless. He wore the same wrinkled sweater until someone forced him to change. These eccentricities are charming in retrospect. They make the genius seem accessible. But for people living with him, they were probably irritating. He played violin. Not exceptionally but competently. Mozart was his favorite. He said Mozart composed music so pure it seemed to have always existed in the universe, waiting to be discovered. Exactly how Einstein saw physical laws. Not invented. Discovered. Revealed. For him, doing physics was like making music. Seeking hidden harmony. Underlying structure. The beauty that makes equations true even before verifying them experimentally. He sailed. He had a small sailboat on a lake near Princeton. He spent hours alone on the water. No motor. Just wind and sail. He said sailing helped him think. The gentle movement. The sound of water. The need to pay attention to wind but not too much. Was meditative. And he frequently ran aground. He wasn't a good sailor. He got distracted. He'd start thinking about some physics problem and forget he was sailing. Locals would find him stuck on shoals, lost in thought, puzzled about how he'd gotten there. He smoked a pipe constantly. His Princeton office smelled of sweet tobacco. When doctors told him to stop smoking, he refused. He said smoking contributed to calm and objective judgment in all human affairs. It's doubtful. But he enjoyed the ritual. Filling the pipe. Lighting it. The pauses while smoking, creating space to think. Eventually he stopped when health worsened. But he missed the ritual more than the nicotine. He loved children in abstract ways. He enjoyed explaining scientific ideas to them. He answered letters from children who wrote with questions. His responses were charming, patient, clear. He treated children as serious intellectuals just without training yet. But with his own grandchildren he was distant. He visited. He brought gifts. But he didn't play with them. He wasn't emotionally present. As if he could be warm with abstract children but not with specific children who needed his attention. There's a story. Einstein walking through Princeton. A neighborhood child is struggling with mathematics. The mother asks Einstein for help. He accepts. He sits with the child. He patiently explains. The child understands. The mother is thrilled. Afterward, the child tells his mother that Einstein is a very good teacher but a poor mathematician because he has to check everything several times. Einstein hears this and laughs. It's the best description of his method. He wasn't a fast calculator. He wasn't a prodigy who saw answers instantly. He worked slowly. He checked obsessively. He made sure he understood every step. His genius wasn't speed. It was depth. This is the complexity the myth erases. The myth needs simplicity. The hero who was always right. The genius who saw clearly while others were blind. But reality is more interesting. Einstein was frequently wrong. His first attempt at general relativity, published in 1913, had errors. He had to retract. He spent 2 more years working. When he finally published the correct version in 1915, another mathematician, David Hilbert, was working on almost identical equations. Hilbert could have published first. He didn't. He recognized Einstein had the physical vision first. The equations were just formalization. But it was close. Einstein didn't work in a vacuum. There was competition, collaboration. The real scientific process is more complicated than the solitary genius narrative. And after 1925, after quantum mechanics emerged, Einstein became progressively marginal. Still respected, still famous, but no longer at the forefront. His younger colleagues were exploring new territory while he persisted in objecting to quantum theory's foundations. Not because he was stupid. His objections were sophisticated. They pointed out real interpretation problems. But the theory worked. Predictions were correct. And eventually, science advances not because old scientists change their minds but because they die and new generations accept new ideas as obvious. Einstein knew this. He quoted Max Planck, "A new scientific truth does not triumph by convincing its opponents, but rather because its opponents eventually die, and a new generation grows up that is familiar with it." It was self-consciously ironic. He'd been the young revolutionary. Now he was the old guard. The cycle continues. So who was he really? Not the icon. Not the tongue out. Not E equals MC squared. Not the wild hair. But the real man at the center of all that. He was someone who couldn't stop asking questions. That's the central characteristic. Obsessive curiosity. From the compass at 5 years old to the unified field equations on his deathbed, 70 years of incessant questioning. What? Oh, what if? He wasn't particularly happy. He had moments of joy, discovery, the eclipse confirmation, the satisfaction of solving a problem. But overall, his life was solitary, emotionally isolated. He spent more time in his head than in the world. That's what this level of concentration requires. Withdrawal. Prioritization. Einstein chose to understand the universe over understanding people. It's a trade-off. He made the universe clearer for all of us. But his personal world was often dark and confused. Was this necessary? Is emotional isolation the price of genius? Probably not. There are brilliant scientists who are also good fathers, good husbands, emotionally present people. But Einstein specifically seemed to need that distance. For him, human relationships were complicated, unpredictable, chaotic. Equations were clean, logical, comprehensible. Taking refuge in physics was taking refuge from human mess. And this brings us to an uncomfortable truth. We admire Einstein. Correctly. He changed how we understand reality. But we shouldn't admire all aspects of his life. We shouldn't emulate him completely. We should admire his curiosity, his persistence, his willingness to question orthodoxy, his search for truth, but not his emotional negligence, not his treatment of those closest to him, not his inability to be present. The myth doesn't allow this complexity. The myth is black or white, heroic or villain, but reality is gray. Einstein was both. More precisely, he was human, with extraordinary gifts and ordinary flaws. And that should be the lesson. That you don't need to be perfect to contribute. That your flaws don't invalidate your achievements. That you can do something important even if you're not a saint. The narrative voice here becomes reflective, almost philosophical but without losing human tone. As if we're sitting in Einstein's study, looking at his notebooks and trying to understand not just what he thought but who he was. The camera metaphorically zooms in. We're not looking at the historical panorama. We're looking at wrinkles in his face, tired eyes, ink-stained hands. There were days at the end where he simply sat, looking out the window, no longer working on equations, just thinking. Helen Dukas, his secretary who stayed with him until the end, would find him like this. She'd ask if he needed anything. He'd smile. Just thinking, he'd say. About what, she never asked. Perhaps about physics. Perhaps about regrets. Perhaps about nothing in particular. Just an old man reflecting on a long and complicated life. Did he consider himself successful? Probably. He'd achieved more than most. He'd seen his theories confirmed. He'd received all honors science can bestow, His name was synonymous with genius. But he'd also failed. The unified theory didn't exist. The atomic bomb did. His personal relationships were mostly failures. His children saw him as distant. His wives as absent. His closest friends loved him but also found him exasperating. On balance, was it worth it? That's the question. Was the personal cost justified by scientific achievement? Einstein would probably say yes. He had no choice. He didn't choose to be this way. He simply was. He couldn't not do physics as he couldn't not breathe. It was his nature. Blaming him for following his nature is like blaming water for flowing downhill. It's what it does. But that's Einstein's perspective. From other perspectives, Milevas, Edwards, Hans Alberts, the equation changes. Their lives were harder because of Einstein's choices. Their suffering was real. And they received no compensation in the form of scientific legacy. They can't share E equals mc superscript 2s glory. They only bear the cost. This is the tension that remains unresolved. The genius who contributes immensely to abstract humanity while harming specific humans. It's not unique to Einstein. It's a common pattern. Artists who create beauty while their families suffer. Leaders who achieve great things while their personal lives are disasters. As a society, we tend to forgive. To say art justifies harm. That achievement compensates cost. But for whom? Not for the harmed people. There's no easy resolution here. Only recognition. Einstein was complex. He did great good. He did real harm. Both things are true. We can admire his physics while lamenting his imperfect humanity. Indeed we must, because the alternative is hagiography. And hagiography teaches nothing except that saints are beyond us. But Einstein wasn't a saint. He was a person. And if a person can rewrite physics, then perhaps other people can too. With their own flaws, their own complications, still capable of contributing. Now the narrative must shift. Move away from the specific man. Away from Einstein at his desk, Einstein with his family, Einstein with his pipe. Broaden out. Look at what his ideas mean. Not just for physics, for everything. For how we think about reality itself. This is the transition from part 18 to 19. From Einstein the man to Einstein the concept. From biography to philosophy. But keeping the tone accessible. Not abstract. Concrete but broad. When Einstein changed our understanding of time, he changed more than physics. He changed metaphysics. For millennia, humans assumed time was like a river. It flows in one direction. From past to future. The same for everyone. A second for you is a second for me is a second for anyone anywhere in the universe. It's common sense. It's direct experience. It's obviously true. Except it's not. Einstein demonstrated time is elastic. It stretches and compresses depending on how you move. Your now isn't my now if we're moving differently. Your past could be my future from another perspective. There's no universal now. No present moment the entire universe shares simultaneously. Simultaneity is illusion, an artifact of our low velocities. This destroys deep intuitions. When you see a star, you see it as it was. Light takes time to travel. You see the star's past. But what is the star doing now? The question has no answer. Now means nothing at stellar distances. We could say, now in Earth's reference frame. But that's arbitrary. From another reference frame, moving fast relative to Earth, the star's now is different. Both are correct. Both are real. Or neither is. The concept of now doesn't correspond to anything absolute in the universe. This realization is vertiginous. We spend our lives assuming the present is real. That the past was real but no longer exists. That the future will be real but doesn't exist yet. Only the present has existence. But Einstein says no. Past, present, and future are equally real. They're locations in space-time. Like north, south, east, west are locations in space. Moving from past to future is like moving from north to south. You change your location, but all locations exist simultaneously. This is called eternalism or the block universe. All of space-time from Big Bang to universe's end exists as a single four-dimensional structure. Your birth exists. Your death exists. They're at different locations in time, but both are equally real. From a perspective outside time, if such a perspective were possible, your entire life is visible at once. Like a book where all pages exist simultaneously though you read them sequentially. The implications are profound. If the future already exists, do we have free will? If all our actions are already determined, already exist in spacetime's future, are we just executing a pre-written script? Or more precisely, if there's no real division between past and future, if everything is equally real, what does it mean to choose? Philosophers have debated this since Einstein published Relativity. There's no consensus. Some say free will is compatible with eternalism. That choosing is part of causal structure. That the fact the future exists doesn't mean it's determined independently of your choices. Your choices are what determine it. Others say it's illusion. That we feel free but we're really following paths already laid out in spacetime. Einstein personally was a determinist. He believed the universe was a system of cause and effect. That if you knew all particles' positions and velocities, you could calculate the entire future. It's a Newtonian perspective. But Einstein maintained it even against quantum mechanics, which says the universe is fundamentally probabilistic. For Einstein, God doesn't play dice. The universe has order, laws, structure, not chaos, not chance. Ironically, his own theory, general relativity, permits strange things. Closed time-like curves. Paths through spacetime that return to their starting point in time. Theoretically, you could travel to the past. The equations allow it. It requires exotic conditions. Matter with negative energy density. Probably impossible. But not absolutely forbidden by physics laws. If time travel is possible, paradoxes emerge. The grandfather paradox. You travel to the past and kill your grandfather before your father is born. So you're not born. So you don't travel to the past. So your grandfather lives. So you're born. It's a logical loop. Contradiction. Most physicists think something must prevent this. Perhaps self-consistency is a physical law. Perhaps you can only do in the past what you already did. Perhaps time travel isn't really possible and the mathematical solutions permitting it are curiosities without physical realization. But the fact these questions can be formulated shows how profoundly Einstein changed our thinking. Before relativity, time was simple. Now it's complicated, rich, full of strange possibilities. And this isn't just philosophy. It affects how we do physics, how we think about causality, how we interpret experiments. In quantum mechanics, there are experiments where the future seems to affect the past. Delayed choice. You decide how to measure a particle after it's passed through apparatus. But your future choice seems to determine what happened in the past. The particle behaved as wave or particle depending on a choice you haven't made yet when it passed. It's strange. It's counterintuitive. But it's what experiments show. How to reconcile this with relativity? It's unclear. It's one of the open problems. Quantum mechanics and general relativity are both extremely successful theories. But they're fundamentally incompatible. They operate under different assumptions about time's nature, space's nature, reality's nature. Unifying them is the grand challenge. The problem Einstein couldn't solve. The problem we still haven't solved. And then there's space. Einstein changed space as much as time. Before relativity, space was a container. Empty. Things existed in space. They occupied locations. But space itself did nothing. It was passive background. Neutral stage where physics's drama unfolds. Einstein said no. Space is an actor. It has properties. It can curve. It can stretch. It can compress. Gravity isn't a force acting through space. It's space's curvature itself. Masses don't attract other masses. Masses curve space around them and other masses follow the curvature. It's difficult to visualize. We're trapped in three spatial dimensions. We can't see from outside. But imagine a stretched sheet. It's two-dimensional, flat. Now place a bowling ball in the center. The sheet sinks. It curves. Not in a fourth spatial dimension. The sheet is still two-dimensional, but its geometry has changed. A straight line drawn on the curved sheet is no longer the shortest distance between 2 points. Curvature alters geometry. That's what masses do to space. They curve it, and curvature alters how things move. Planets orbit not because there's a force pulling them, but because they're following straight paths, geodesics, in curved space. It's like walking straight on Earth's surface. You end up going in a circle, not because a force is deflecting you, but because the surface itself is curved. This idea that geometry is physics is revolutionary. For millennia, geometry was mathematics. Abstract, Platonic. It existed in a world of ideas. The Pythagorean theorem is true in Euclidean geometry independent of whether anything physical exists. But Einstein made geometry physical. Spacetime's geometry is determined by matter and energy, and it determines how matter and energy move. It's not abstract. It's as real as a rock. More real because rocks are made of curved space. This changed mathematics too. Suddenly, non-Euclidean geometries, which had been abstract curiosities, became physically relevant. Riemannian geometry, spaces with curvature, exotic topologies, not just mental games, descriptions of reality. Mathematicians had to talk with physicists. Physicists had to learn sophisticated mathematics. The division between disciplines blurred. In philosophy, Immanuel Kant had argued that space and time are forms of intuition, preconditions for experience, not things in themselves but the framework our minds impose on reality to make sense of it. Three-dimensional Euclidean space and linear time are, in Kantian philosophy, a priori categories, not learned from experience but necessary to have experience. Einstein showed Kant was wrong. Space isn't Euclidean. It's curved. Time isn't absolute. It's relative. These aren't mental categories. They're physical properties of the universe, discovered empirically, not deducible a priori. Kant assumed Newtonian physics was necessarily true. It turned out to be approximation, useful at low velocities and weak gravitational fields, but not fundamental. This is a lesson about philosophy. Even the most convincing arguments, ones that seem logically necessary, can be wrong. Reality isn't obliged to conform to our intuitions. It isn't obliged to be comprehensible in ways that seem natural to us. It is what it is, and our task is understanding it on its own terms, not forcing it into preconceived categories. Einstein understood this profoundly. That's why he could think beyond Newton. Not because he was necessarily smarter, but because he was willing to abandon intuitions, willing to accept that time might not be absolute, that space might not be flat, that reality might be strange. And it turns out reality is strange. Every time we look deeper, stranger it becomes. Particles that are also waves, cats that are alive and dead, instantaneous action at a distance, multiple universes, black holes that evaporate, energy that emerges from vacuum. None of this is common sense. All is counterintuitive. But all is, as far as we can tell, true. Einstein's relativity opened the door. It showed we can be fundamentally wrong about reality's basic structure. That things seeming obvious, absolute time, flat space, universal simultaneity, can be approximations, illusions generated by our limitations. We live at low velocities, weak gravitational fields. So time seems absolute. Space seems flat. But they're not. And once you accept you can be wrong about such fundamental things, everything is at stake. Every assumption is questionable. Everything must be verified empirically, not assumed philosophically. This is the epistemological lesson. How we know what we can know. Einstein showed the scientific method, experiment plus theory, can lead us to truths we'd never have imagined. That reality is discoverable but not obvious. That mathematics is an incredibly powerful tool for understanding the universe. That nature speaks mathematical language, as Galileo said, but more sophisticated language than Galileo imagined. And this leads to final reflection. Why is the universe mathematically comprehensible? It's a deep mystery. Physicist Eugene Wigner called it the unreasonable effectiveness of mathematics. We invented mathematics to count sheep and measure fields. But it turns out the same mathematics describes planetary motion, light's behavior, space-time structure. What? One answer: because the universe is mathematical. Physics's laws are really equations, not approximations, not descriptions, but reality itself. The universe is executing code, and we've discovered parts of the code. This is Platonic vision. Mathematics is more real than matter. Matter is manifestation of mathematical structures. Another answer: because we're part of the universe. Our brains evolved in this universe. They're made of its laws. So naturally, the structures we find intelligible, mathematics, reflect the universe's structures. Not because the universe is mathematical, but because our minds are universe products and therefore resonate with its structure. Or perhaps both, or neither. We don't know. But the fact we can ask the question, that we can be conscious of our own understanding, is extraordinary. We're pieces of the universe that have become conscious, that can reflect on themselves, that can wonder where they came from and where they're going. Einstein facilitated this. His work expanded the boundaries of what we can understand. Before him, the universe was smaller, simpler. After him, it's vast, complex, full of wonders. Black holes where time stops. Gravitational waves that ripple space itself. The possibility the universe is one of many. That the Big Bang was a bounce from previous collapse. That space and time themselves might be emergent, not fundamental. These ideas are all rooted in relativity. All use the framework Einstein built. Some go beyond what he'd have accepted. But they use his tools, his equations, his vision that spacetime is dynamic, malleable, interactive. Without Einstein, we'd still be in Newton's universe. Cosmic clock. Eternal mechanism. Predictable and boring. Thanks to Einstein, we live in a narrative universe. With beginning. Probably with end. With history. With unique events. With possibilities that will never repeat. The universe had infancy, the Big Bang. It has middle age now, forming galaxies and stars. It will have old age when stars go out and black holes evaporate. And finally, perhaps heat death. Cold, dark, empty. Or perhaps not. Perhaps something else. We don't know yet. But we know the universe is more than stage. It's participant. It's the story being told. And we, small, ephemeral products of 13.8 billion years of cosmic evolution, are the part of the universe that can tell the story, that can understand it, that can marvel. Einstein gave us that. Not just equations, not just predictions, but a new way of being in the universe, conscious of our smallness, conscious of our insignificance on cosmic scales, but also conscious of our capacity to understand. That a hairless ape on a small planet orbiting an average star can decipher laws governing galaxies. It's absurd. It's impossible. It's miraculous. And it's true. Now the light fades. It's time to close. To bring the narrative to conclusion. Not with answers. With questions. With reflection. With the sense we've traveled long distances but also know there's more distance to travel. This is the poetic closing. The final metaphor. The image that remains. Imagine this. It's night. You're outside. Far from city lights. The sky is clear. Stars are bright. Countless. Millennia ago, humans looked at this same sky and saw gods. They saw destinies. They saw stories of heroes and monsters projected in constellations. The universe was small. Earth was center. Everything revolved around us. We were important. Then came scientists. Copernicus moved us from the center. Earth orbits the sun, not vice versa. Galileo saw moons orbiting Jupiter. Not everything revolves around us. Newton showed the same laws that make apples fall control planets. There's no separation between heaven and earth. Everything is matter following rules. Darwin showed we're not biologically special. We're animals, descendants of simpler animals, products of evolution, not special creation, not divine souls put in bodies, just organisms. Complex, yes, but not fundamentally different from everything else that lives. And Einstein showed space and time themselves are relative. There's no privileged viewpoint, no universal reference frame. Your perspective is valid. Mine is valid. But neither is absolute. We're observers among many, in a universe that doesn't need observers, that existed before us, that will exist after. It's humbling. Every discovery makes us smaller, less central, less special. And yet it's we who make these discoveries. It's we who understand. Small, ephemeral, but conscious, capable of comprehension, capable of wonder. Einstein understood this. The man who chased light taught us the universe isn't made of certainties, but of questions. Every answer opens new questions. Every discovery reveals new mysteries. It's not frustrating. It's beautiful, because it means the search never ends. There's always more to learn. There's always frontier beyond. When he was a child, Einstein held a compass. The needle moved without being touched. Something invisible acted. And he dedicated his life to understanding the invisible. The forces, the fields, space-time structure. He went from simple question, why does the needle move, to cosmic questions. Why does the universe exist? Why does it have these laws and not others? Where does time come from? Where is it going? He didn't answer everything. No one can. But he moved the conversation forward. He expanded the territory of the known. And in doing so, he expanded the territory of the unknown. Because only when you know something can you know what you don't know. Informed ignorance is deeper than simple ignorance. There's a final image. Old photographs of Einstein at his desk. Surrounded by papers. Equations everywhere. Open notebooks. Cold coffee cups. Full ashtrays. The disorder of a mind working intensely. And at the center, Einstein. Tired, but still thinking. Still calculating. Still searching. Until the end. On his nightstand in the hospital when he died, there were pages of equations. His last search for unified theory. Unfinished. Never finished. But the effort is what matters. Not final success. But willingness to keep searching even when answers hide. Even when the problem seems impossible. Even when you know you might not live to see the solution. That's chasing light. Not necessarily catching it, but pursuing it, following it wherever it leads. Even if it leads to shadows. Even if it reveals horrors like the bomb. Because knowledge is a double-edged sword. We can't have only the good side. We can't know how the universe works without also knowing how to destroy it. The power to create is the power to destroy. They're inseparable. Einstein lived this contradiction. He spent first half of his life revealing beautiful truths. Second half warning about consequences. There's no resolution. There's no way to put the genie back in the bottle. Once we know something, we can't unknow it. Knowledge is irreversible. So what do? Do we stop searching? Do we stop asking questions for fear of answers? Einstein would say no. Knowledge itself isn't the enemy. Ignorance isn't virtue. The problem isn't that we know too much. It's that our wisdom hasn't grown with our knowledge. We know how to split atoms. We don't know how to live together without war. We know how to manipulate genes. We don't know when to stop. We know how to build artificial intelligences. We don't know how to ensure they work for our benefit. Progress doesn't consist of conquering reality, but of learning to imagine it better. That's the phrase that resonates. Not conquer, not dominate, but imagine, understand. Science isn't war against nature. It's conversation with nature. We ask a question. Nature answers. We ask another question. And so it continues. Infinite dialogue. Never finished. Always evolving. Einstein initiated a conversation we still continue. About time. About space. About what it means to exist in this particular universe. Each generation adds more. Sees farther. Asks more sophisticated questions. But fundamental questions remain. Why is there something instead of nothing? Why is the universe comprehensible? What are we that we can wonder about ourselves? There are no final answers. Only increasingly better approximations. Only increasingly deeper understanding. And perhaps that's enough. Perhaps meaning isn't in reaching final destination. It's in the journey. In the discovery process. In the moment of understanding when something dark becomes clear. When an equation that was confusing suddenly makes sense. When you see a connection no one saw before. Einstein had many of those moments. Time is relative. Space is curved. Gravity is geometry. E equals mc squared. Each was revelation. Each changed everything. And each raised new questions. Better questions. Deeper questions. That's the legacy. Not the specific answers. Those will eventually be refined, modified, perhaps replaced. Quantum mechanics has already modified our understanding. A future quantum gravity theory will modify more. But the spirit, the willingness to question, to imagine, to think beyond the obvious, that spirit remains. That's what Einstein gave us. Not just new theories, but new way of theorizing. New courage to question even the most fundamental truths. Look at the stars again. The light you see left years ago. Decades. Centuries. You're seeing the past. And that light traveled through curved space-time. It was deflected by gravity of stars and galaxies between us. It was stretched by universe's expansion. It arrived at your eye after a journey that began before you were born, perhaps before your species existed. And still you can see it. Still you can understand it. You can calculate how far it is, how hot it is, what it's made of. All because Einstein and others like him showed us how to read the universe's book. How to translate light into knowledge. How to see not just with eyes but with mind. That star you're looking at doesn't know you're looking. It doesn't care. It will keep shining or explode or go out independent of your attention. The universe is indifferent. It wasn't made for us. It has no purpose regarding us. It simply is. And we, cosmic accident, statistical miracle, are here for a moment. Briefly conscious. Briefly capable of understanding. It's in that brief moment where we make meaning. We don't find it. We make it. Choosing what matters. Choosing what to seek. Choosing how to use our limited time. Einstein chose to understand. He chose to chase light. Metaphorically and literally. And that choice reverberated through decades. Changing how everyone sees the universe. Changing what's possible. Changing who we are. Because we're not just our bodies. We're our ideas. We're our understandings. We're the conversations we have with the universe and with each other. Einstein is part of that conversation. His voice still heard. His ideas still relevant. His questions still unanswered completely. And perhaps that's most important. Not that he solved problems, but that he showed problems can be solved. That the universe yields to reason. That mathematics works. That we're capable of more than we thought. That a human, fallible and complicated, can touch the eternal. Can see laws that were operating before life began and will continue operating after life ends. We're all in the same universe. All subject to the same laws. All the particles in our bodies following Einstein's equations. Falling through curved space-time. Moving toward future at the rate of 1 second per second. Aging because time is an arrow. Dying because entropy always increases. But while we're here, while we're conscious, we can do what Einstein did. We can ask. We can imagine. We can seek to understand. We don't need to be geniuses. We don't need to revolutionize physics. We just need to keep curiosity alive. Keep the question alive. Because every question, no matter how small, is an act of resistance against darkness. It's saying the universe matters. That understanding matters. That we exist not just to survive but to comprehend. And when finally the light fades, when our moments end, When we become past that others will look back to, the questions remain, the ideas remain, knowledge remains, passed from mind to mind, from generation to generation, Einstein to his students to theirs. And so until now, until you, reading this, thinking about this, becoming part of the conversation, that's the light Einstein chased. Not just photons traveling through vacuum, but the light of understanding, literal enlightenment, seeing what was hidden, knowing what was unknown, and sharing that, so others can see, so light spreads, so darkness recedes, one discovery at a time. The universe doesn't promise to be fair. It doesn't promise to be kind. It doesn't promise to make sense. But it promises us this, that it's there, that it exists, that it can be known. And that promise, that possibility of knowledge, is a gift. It's what makes existing more than just waiting for death. It's what makes life adventure, mystery, quest. Einstein lived that quest completely, with all his human flaws, with all his errors and regrets, but without compromise in the search itself, until the end, until the equations on his nightstand, until his last breath, still asking, still imagining, still chasing light. And the light continues. It doesn't stop. It travels through space at invariant velocity. It traverses time according to equations Einstein derived. It connects past with present with future. It connects distant stars with our eyes. It connects the Big Bang's moment with this moment. Now, when you read these words, when you think these thoughts, when you decide what to do with your small portion of conscious time in this vast and different universe, choose wisely. Choose with curiosity. Choose with wonder. Because the universe waits to be understood. And you're part of the universe trying to understand itself. You're what Einstein was. You're what we all are. Light, temporarily conscious. Asking. Always asking. What? How? What does all this mean? The answers matter less than the questions. Because questions keep us searching. And while we search, while we keep chasing light, we're not lost. We're on the path. The same path Einstein walked. The same path all truth seekers have walked. Forward. Toward understanding. Toward light.